So Revati ma'am has joined, huh? Anil sir?
Yes, ma'am.
Joined, madam.
Okay, okay. So good evening, sir. So good evening to all the participants. Yes, sir. So we warm welcome you for our esteemed guest who graciously accepted our invitation to be a part of this 6-day ATAL sponsored faculty development program on VLSI design innovations for defense applications. So we are honored to have you with us today, sir. Now I request Mrs. P. Revati, Assistant Professor of EC Department, to introduce the guest.
Thank you, ma'am. Good evening, sir.
Hi.
Good evening to all. It's my pleasure to introduce today's resource person, Mr. A. Geethanath. Sorry. Mr. Geethanath is an analog design manager based in Elst, Netherlands, where he leads a team of analog engineers. He oversees product roadmaps and innovation for the next generation voltage translators. With 17 years of experience in analog and mixed signal design, Geethanath holds a postgraduate degree in VLSI systems from the National Institute of Technology, Tiruchirappalli. From 2007 to 11, he was with On Semiconductors, Bangalore. He started his career as an analog and mixed signal design engineer. He contributed to spread spectrum EMI reduction clocks using charge pump PLLs, developing charge pumps, high-speed drivers, and PLL designs. From 2011 to 16, he was with IBM. He worked as a staff R&D engineer focused on resonant clocking, clock distribution networks, and transmitter clock or data paths for PCIe Generation 3 and Generation 4. He also designed duty cycle detection and correction circuits for high-speed clocking application. In 2016 to 17, he was with Intel. He joined in Intel as an analog engineer, contributing to display port circuit design before transition to the Netherlands. From 17 to 24, he was with Voltage Translator Product Group. In 2017, he joined as a principal design engineer, developed glitch-free power sequencing for voltage translators. In 2020, he became a design lead, managing the I2C portfolio and developed the SIM card translator architecture, now widely used in modern phones as an interface between SIM cards and microcontrollers. In 2021, he promoted to architect, leading the development of the I3C bridge product. In 2024, he promoted to R&D design manager, driving innovation and defining the product roadmap for voltage translators. His career reflects a strong focus on innovation and leadership in analog and mixed signal design. Now I would like to welcome Mr. Geethanath sir and request to take over the session. Thank you, sir.
Hi, thank you for the introduction. Let me share my screen. Before that, I would just like to add one small thing. I born and brought up in Andhra Pradesh. I'm basically from Nellore. I studied in Nellore. Still, my parents are living over there. Yeah, I frequently visit India every year. Okay, basically, I think I have on the screen. Let me see. Can share the. Going to the screen.
Just now the screen was visible, sir. Now it is not visible.
Yeah. Actually, it's going on multiple screens. I'm just trying to find out. Yeah, what is the reason? Okay. Anyways, I'll move to the other screen. It's better. Okay. Okay, so you can see my screen, right?
Yes, sir.
That's great. Just let me just visual. Okay, so thanks for the opportunity and also for the introduction. When Sivasangri asked me about a topic to be chosen, I thought it's a good to introduce about I3C, which is new to the market, and also it brings a lot of opportunities for the lecturers and professors to look into some interesting projects, which are mixed signal projects. Unlike I2C, it's a small, less complex, low complex one, but I3C is a quite complex. So I thought it's really good to introduce. I wanted to choose the other ones also, like voltage translators and applications, but still I found out that this is a good one to talk about so that the students also learn about what is I3C and what are the applications probably in the coming years when I3C picks up. It's going to be a really interesting protocol in the industry. If I'm not wrong, then I3C is not part of any of the curriculum, I think. Can someone answer? Did anybody worked on I3C in recent years?
It is not in the part of the curriculum, sir.
Okay, nice. Then it's a good opportunity that I would like to introduce about basics. So basically, I worked on I3C and one of the important product, which I cannot disclose in this session. So I used all the material. It's only development from my side using MIPI I3C standard, which is open to download. Even you can also request through MIPI about I3C protocol, and you can get it in your email. So I used it from the MIPI website, so that I don't disclose anything from the company side. At the same time, I would really like to share the knowledge that I have gained in the recent years from I3C. So we did a lot of research about I3C, and also we were also some of the time we were having membership in MIPI, which is widely promoting I3C in the industry. So based on my knowledge, I developed the slides that I'm going to present now. Okay. So the agenda is something like this. So I2C, it's already in the 40 years in the semiconductor industry. But it gained really wide applications and also widely appreciated in many systems. Um, However, it also have limitations. So, and it's time to replace I2C with some other protocol. Then maybe showed really interest towards I3C. By the way, I2C was developed by Philips, which was our former company, Nexperia. Nexperia was a spin-off from NXP. NXP was spin-off from Philips. So originally, I2C is from Netherlands. So it's already 40 years in semiconductor industry. However, it is widely used. It's open source, I think. So first I'll start with I2C protocol and applications. So people who don't know about I2C protocol, I just introduce some slides. And I would introduce some of the Nexperia's I2C products, which we have developed in recent years. Then what are the features of I2C? Then I'll go to features of I3C, then I3C modes of operation. And most importantly, I would like to really focus on these concepts, which are distinguishing features of I3C against I2C, dynamic addressing, IBI, hot join. After that, I will explain some of the electrical characteristics of I3C. So these are the protocol related stuff. When it comes to what voltage range I3C can support, what frequency I3C can support, these are all listed by MIPI. So this is properly specified at this moment. At the same time, I3C also comes up with some limitations. So I would like to talk about limitations also. What are the limitations of I3C? How it's going to impact I3C's future? That's also we can discuss. Okay. In between, anyone has any question, you can always interrupt me. I would like to encourage an interactive session here so that you can ask the questions, and also I will try to come up with answers. Okay. In case if I'm not able to answer the questions, then I will go back and respond in a few days. Okay. Yeah. Let me go to the next slide. So I2C protocol, I will explain here through a simple example. This example is a temperature controller. Basically, I2C is a protocol that communicates from the master to slave. Slave can be any device like a temperature sensor or gyroscope or accelerometer, anything that has the ability to support I2C, which is simple protocol. So you can see here, this is Arduino microcontroller that can interact with temperature control through I2C commands. Basically, it's a simple application. It's a temperature sensor, and master wants to read the temperature data from temperature sensor, and it can do with the I2C protocol. If it doesn't require any external data or any other bus, because the data can be a simple data, it can be binary coded. It doesn't require really a very high-speed communication. So simple I2C can be useful here to fetch the data here. Okay. So what I2C protocol? Basically, the master is responsible for initiating the communication, and master sends the address that's called the address of the temperature sensor, and each slave on the I2C bus has an unique address. In this case, the temperature sensor has his own address, which is a 7-bit address. Let's assume 076. When master sends an address here, and temperature control responds with an acknowledgement, that's called acknowledgement here. It says that, okay, the address that is sent by the master is matching with the address of the temperature controller, and the temperature and the master can send the data, and also master can receive the data. Okay. Here, master can send the data, and also first it sends the address, then master can send the data to configure the temperature sensor. Let's assume it wants to read it in a 2 bytes of information. Then it can say that, okay, then the configuration register is 2 bytes. And if it wants to send in a degree centigrade or Fahrenheit, then it can mention this data too, like that. The data can be written from the master, so that temperature sensor can be programmed properly. At the same time, you can see here, once the temperature sensor is configured, then temperature sensor can generate the data. Whenever master wants to read, then temperature sensor gives back the data. It's very important that please notice here, temperature sensor can always respond. However, if master doesn't want to read, then temperature sensor cannot generate any data. Only when master wants to read, then only temperature sensor can read the data. That means temperature sensor doesn't have any ability to say that there is a temperature change and please read back. That's not the case. Okay. So always master has to send the clock, then temperature sensor can generate the data, and it can read back by the microcontroller. Okay. So you see here, this is for the write operation. That means master can send the data. So this is from the master to, okay. By the way, controller is nothing but master, and target is nothing but slave. Okay. These two terms are important in I3C. I3C calls master as controller and slave as target. So controller, in the sense, it's a master. So the gray color shadow here, that is the communication from the master to slave, or controller to target. At the same time, acknowledgement, this the white color one, that is acknowledgement. Every byte of information, acknowledgement comes back from the temperature control saying that temperature controller accepted the data successfully. This is for the write operation. And for the read operation, you can see here, if master wants to read the data from temperature controller, then it can set the read write bit 1. In the previous case, it is 0. And master can read the data from the temperature controller. And the temperature controller sends the data immediately. Okay. So here the communication is completely controlled by the master. That means slave doesn't have, or target doesn't have any control over the communication. It's only the master that can control the communication. That is the one of the drawback of I2C. And you can see here, this is the combined format where the complete read operation is described. So first it starts with write operation followed by the read operation. So this is the basic functionality of the I2C. And based on the application, customer or user can modify the next bytes of information, and user can extend these bytes to any number of bytes. Let's assume some customer wants to configure 8 registers. Then a customer can extend this protocol to 8 bytes of information. So like that, this is a generic protocol, and any number of bytes of information can be transmitted, can be received easily. So that's the reason I3C has really flexible, and it's widely accepted in the industry. Okay. And also here there are few important things in the I2C protocol. So I2C protocol always starts with a start condition and it stops with a stop condition. This is also a very good thing proposed by Philips in the early days, that this can be easily recognized by any target, and also timing also carefully proposed. So still, you can imagine, even 40 years, after 40 years also, still the protocol is used. So the robustness of the proposal is really good here. Okay. Any question here? If not, I'll go to the next slide. So another application. So in the previous application, the master uses simple I2C lines to communicate the data and get back the data. But imagine a camera that is communicating with the application processor. However, like the modern cameras can come up with a lot of data, so the quality of the picture is very, very, very good. So I2C cannot handle such kind of high-speed data. So there is a protocol CCI, so that is dedicated for the camera protocol, where I2C simply used just to activate the communication. Once the communication is activated, then immediately the high-speed data link will get activated, and the processor receives the data from the camera. That means there is a dedicated channel that sends the data to the receiver. However, I2C doesn't participate doesn't do any activity for the data communication. It's a completely dedicated data bus, which is independent. So that means you can already imagine this 400 kilohertz is a limitation of the I2C. That means for exchanging the high-speed data, it's not at all useful. So it should be handled with some other bus. It's the same case with many applications where I2C is just used for configuring and startup and stopping the communication. So this protocol, and also in slow speed applications, I have seen many slow speed application I2C is used. Let's assume if someone wants to turn on the microcontroller, then still I2C is used as a start bit to turn on, turn off, and turn on the microcontroller. So it's also used in the power saving modes, and I will show in the next slides what are the applications widely used in I2C. Okay. Any question? If not, I'll go to the next slide. Okay, so basically, it's also important to see what.
Excuse me, sir. Sorry for interruption.
No problem. Yeah.
One of the participant is asked one question, sir. one of the participant asked one question.
Mhm.
That question is, in which aspects of I2C protocol is robustness good for communication?
In which protocol? Sorry.
In which aspects of I2C protocol is robustness good for communication?
Okay, okay. That's a good question. There are many aspects here. First thing is large load capacitance. Okay, so that means it is used in the server application where I2C supports up to 550 picofarad. That's one of the important thing. Second thing is address arbitration. That means many I2C slaves can coexist on the bus. I'm going to discuss in the next slide. Second thing. Third one is since it's a generic protocol and also with a proper timing it is defined. So failing of the protocol can be easily debugged. That means if there is a bus stuck, then there are certain methods that I2C proposed to come out of the bus stuck. So also there are applications where I2C can be really used on the wide bus. I'll show you the next slide. So these are the important thing that I2C can be used really widely. Does it answer the question?
Yeah, sir. Good. Yeah, good, sir. Good. Thank you for your clarification.
Okay.
Thank you, sir. Proceed.
Okay. So I2C modes and frequency of operation. So you can see here standard mode, which is 100 kHz and 400 kHz fast mode and FM plus. So most widely used application is 400 kHz because of the timing challenges in 1 MHz. The most important timing challenge is the round trip delay. That means every time the slave has to respond. So that's the reason 1 MHz is not that popular, but 400 kHz is really popular. In addition to these three modes, I2C also proposed a high-speed mode, but it comes up with some extra current source implementation, and it can go up to 3.4 MHz and 3.4 Mbps. Okay, so here also it cannot exceed more than 3.4 Mbps, and it's a limitation of the I2C. So that's the reason. Let me go to the next slide. Okay, any questions here? If not, I'll go to the next slide. So high-speed mode, I2C high-speed mode, you can see there is a these I2C is all fully supported by the open drain drivers. So push-pull is not allowed in I2C bus. And high-speed mode, there is, in case of high-speed mode, a current source is implemented, and current source can be turned off and turned on dynamically. So basically, in case of open drain mode, you can see very slopey rising edges, but very sharp falling edge. And for high-speed mode, the current source is only defined on the clock bus, where clock can be a not push-pull driver exactly, but with a current source ramp up, and ramp down also can be pretty fast. So this is one of the feature that is proposed by the I2C to improve the speed of communication. So you can see here, it's a fast rising edge and fast falling edge. However, there is some time the I2C master should also ensure that it's a open drain slow rising edge here. Okay. So here it's a mixed kind of approach where the current source can be enabled, can be disabled, but it's also recommended for high-speed mode. Let me see if I have no. I think in the next slide I will mention what is the difference between push-pull and open drain. This is the maximum speed I2C can support.
Sorry,
Yes.
sorry for the interruption.
No problem.
Actually, sir, in this waveform, the second waveform. Yeah, second waveform. Yeah, it has some transient as well as changes. In one, I think the second pulse has a transient. Yeah, transient. This if you compare this third one, how it's a variation between this two. This also normally we are having. Yeah. Yeah, one is transient. Second pulse is like a positive edge is gradually increasing.
Correct.
And if you come to the another pulse, it is sharply varying.
Correct.
How
That
this
is because, yes, that's a good question. That's because of current source. In this case, the first pulse, this is RC time constant, right?
Yes, sir.
So you can see there is RP, and that charges the complete bus here on the clock line. So this is defined by the RP and C. So you can see the time constant based on the pull-up resistance.
Yes, I understood, sir. The next pulse?
Next pulse is defined by the current source. That means
only,
in the next pulse,
only current source. We won't bother about R and C.
R also in parallel. However, R contribution is very less, but the C contribution is current source contribution is major.
Thank you, sir. Thank you.
Yeah. Okay. Good question. Thanks. The next one. This is unexperienced I2C protocol products that we developed recently. We were a bit late in the market. However, we tried to define most important products like repeaters, GPIO expanders, switches, multiplexers, and level shifters. One of the questions asked was earlier was, what are the main application of robustness of the I2C? So with this I2C protocol using repeater, it's possible to extend the capacitance, bus capacitance. Let's assume in server application, in backplane application, there is a big load capacitance. And using repeater, it's possible to split the capacitance, and successfully the signal can be regenerated. That means a single pull-up resistor cannot handle the complete bus. In this case, the repeater really helps here. So that is to regenerate the signal. And also, let's assume we have a microcontroller at 1.2 volt, and the slave is at 3.6 volt, and the repeater can level shift and regenerate the signal from 1.2 volt to 3.6 volt. That means it also can act as a voltage translator as well. At the same time, we also have a GPIO expander. You can see in an Xperia portfolio. So the GPIO expander also used to, this is basically a serial to parallel conversion. That means we receive the data serially, and the GPIO expander converts the data into onto the parallel ports. Okay. This can also be a dual supply, but I mentioned only single supply here. But the maximum frequency is 400 kHz. Like I mentioned, most widely used application is 400 kHz. So the maximum load capacitance we meet based on the I2C specification. And the I2C switch, that's also important thing. It also acts as a bus isolation. And at the same time, two or more buses can be connected, slaves can be connected on the I2C bus. Then I2C multiplexer, that is to multiplex different signals and enable multiple switches together. And the I2C level shifters, this is simply level shifting, but it's not a regenerating. So there is a difference between the level shifting and the regenerating. In case of level shifting, it uses a switch-based approach, but in case of regeneration the signal, it completely isolates the I2C bus on the A side and B side. But in case of level shifter, it doesn't isolate the bus. So during low state, the bus is fully transparent. So that's the reason I2C level shifter are really robust in the sense for I2C application. So these are the different products in an Xperia portfolio, which I don't want to discuss now. So let me go to the next slide. So why I3C? Basically, you can simply see a visual inspection here. I2C, this is slow, and wiring is not that complex, but still I2C requires extra lines like interrupt line. in order to communicate back to the controller. Okay, so I2C requires more lines, but it is slow. But SPI is pretty fast because of its dedicated input and output. Whereas in I2C, there is only one line for the data. But in case of SPI, there are two lines for the data out, and master in. These two data lines are independent. So that's the reason SPI is pretty fast. However, there are a lot of channels are there. So I2C, this is a combination of both, where it is faster, as well as it's only 2-channel. So the protocol is so robust that it can solve the problem of complex wiring as well as speed issue with the I2C. Okay. Let's see. Any questions here? Okay. I'll go to the next one. So MIPI I2C features. Why we need I2C over I2C? So basically, I2C is not intended to extend the frequency range. So fundamentally, it is became old, but however, it's widely adopted in the market. So it's very difficult to get rid of I2C, but I2C can be a solution in future to replace I2C. So I2C, the maximum frequency can be 12.5 MHz in the SDR mode, and that means single data rate mode. And during DDR HDR, it can extend up to 25 Mbps. That means it's a double data rate. So the sampling can happen both on the rising edge and falling edge of the clocks. It also supports dynamic addressing. I'm going to discuss in the next slide to solve the problem with the static addressing. Then in-band interrupt, this is also important feature, how I2C solves the problem of complex wiring. Then the hot join, this is also an important feature. That means the bus will not hang something joins dynamically. Multi-controller capability, that means 2 or more controller can coexist on the bus. That's also an important feature. Then multi-lane data support, that means it's possible to extend multiple channels for the I2C. Then target reset without additional wire. This is also an important feature. Let's assume if the bus is stuck, then I2C controller can generate a pattern, and then every I2C target must recognize that pattern and it should reset. So this is also a very good feature. And then the question is, can legacy I2C slaves can communicate with I2C? That's where I2C came up with an option that we will support legacy I2C messaging. This is also a very good feature for I2C. That means in future on the I2C bus, it's also possible to have I2C slave. Okay. Then some of the important feature is CCC. That's common command code. These are the dedicated features or codes defined by I2C, which are really helpful for I2C communication. So there are no common command codes in case of I2C. So I2C introduced some codes which are really helpful for the I2C communication. Then error detection and recovery methods. These are also some extra features available in I2C. Okay. These are the important features. I will compare these features in the next slide. But you can see here I2C as a as a controller. This is a target. So in case of controller, there should be registers. So in I2C, the registers are so simple. But in case of I2C, we require configuration register, PRBS generator, then dynamic address allocation. This is a feature of I2C, which is not part of I2C. IBI detection and IBI management and the hot join management. This is also a feature in I2C, which is not there in I2C. And data packet generator, HDR, that means high data rate can be supported here, and legacy I2C. So at the physical layer, there is also clock and data recovery, and there is a pad that is involved for the communication, bidirectional communication. And for the SCL, it's a simple clock that it can send. So when the controller acts as a slave, then it can be also input to the controller. On the target part, you can see here it's all having same thing. However, on the IBI, it's only management, but not only at the target level, but not at controller level. So here it's a dynamic address capture. That means it cannot generate dynamic address. Only the master and only the controller can generate the dynamic address. Then configuration register, they are by default should be part of target. Then HDR mode support also. These are the fundamental difference between controller and target. So you can see here, this is where I would like to focus on I2C widely. One of your colleague asked me how widely it is used. So you can see it's used in the ADCs, DACs, general purpose IO extender, LED controller, DIP switches, and also the repeaters, what I have mentioned as part of NXPRS portfolio. So these are the I2C repeaters that can extend the bus capacitance. That means, let's assume one customer wants to have 800 picofarad of load capacitance. Then 400 picofarad can be possible on the A side and 400 picofarad can be possible on the B side. So it also can act as a bus extender. Then you can see this as the master controller, and I2C multiplexer and switches can exist, and EEPROMs that's also can exist here. LCD drivers, I2C RTCs, temperature sensor, and most important thing is bridges. Okay, you can see this is a bridge. That means I2C can also interact with other protocol like SPI, UART, and USB. Okay, so it's really a flexible protocol that can be really used as a general purpose. Now coming to I3C. So on the I3C, it's not at the application level diagram, but at the different targets can coexist here on the simple bus. So there can be target 1, target 2, and the I2C target can exist. This is where legacy I2C slave can be attached to the I3C bus. So I3C controller can take care of any I2C product on the bus. Then you can see here I3C also supports with bridging. That means I3C is capable to connect with downstream SPI or I2C or UART device. So I3C has the capability to have bridging function. Then there is a primary controller, and it can also be possible that there is a secondary controller possible in the complex environment. There is also other feature like virtual target. That's also one of the things that we explored as part of our project, but it requires more complex analysis. This is the difference between I2C and I3C. However, both protocols are meant to extend to connect multiple devices on the bus. Okay, that's the fundamental advantage of I2C and I3C. Let me go to the next slide. We have a basic comparison. I put it here. So MIPI I3C, it's a simple two-wire communication. In case of I2C, interrupt is required in order to ensure that slave wants to generate some data. That's possible. So always interrupt is required here. In SPI, there are so many lines are there. So it's a complex wiring. So it's a two-wire, but it's possible to have actually it is 25 Mbps, but in case of multi-lane approach, 33 Mbps is possible. But I need to check this one, why it is 33 Mbps. But on the I2C, like I mentioned, 3.4 MHz is possible and the high speed. But SPI can be really fast. It can be go as high as 60 Mbps also. But SPI is also widely used in the industry. Okay, so considering these, I3C can be a good solution in future, avoiding the complex wiring as well as simple two-wire communication. Okay, we expect I3C can gain more popularity in future. Okay, let me go to the next slide. So I would like to basically compare between I2C versus I3C with a table. So this is this is not this. The I2C doesn't belong to MIPI. Only MIPI I3C belongs to MIPI. The clock speed, like I mentioned, the maximum is 3.4 Mbps, but in case of SDR, it can go to 12.5 Mbps, and the HDR, DDR 20 Mbps, excluding the acknowledgement and payload. Then it's a simple 2-wire, both are 2 wires. Here, the power is high because of the open drain architecture. I will discuss in the next slide why it is higher power. Here it is low due to push-pull, and the SDA also can work as a push-pull, so that high keeper can be disabled. High keeper in the sense, the pull-up resistor can be disabled here. Slave read termination. Master has to end any read operation or write operation, but in case of MIPI I3C, the slave can also end the read operation. Then in band interrupt, there is no capability. I2C, hot join, no capability, but I3C supports both. Built-in commands, there are so many CCCs are there, though, so user can really make use of CCCs to program or to develop any complex project. Error detection, no capability. Here, there are capabilities are there. And then multi-master supports. Here it is primary and secondary controller and targets. The static address, this is the limitation of I2C. That means always I2C comes up with a fixed address for each part. But in case of I3C, it is a dynamically address can be assigned, which is a big game changer here. Okay. Any questions here?
Sir, no questions, sir.
Okay, thanks. Let me go to the next slide. So I think most of you know open drain versus push-pull. In case of open drain, only the NMOS driver is there, and there is a pull-up resistor. That means when the NMOS transistor is on, there is always a current from the supply through resistor and to the ground. But in case of push-pull, there is no high keeper is required. That means pull-up resistor is not required. So here, both NMOS and PMOS can drive the bus here. However, the limitation of the open drain driver is the very weak pull-up. That means RC time constant is the limitation. So maximum frequency is a fundamental limitation with open drain. But push-pull driver, it can possible to have a high-speed communication with push-pull driver. However, I3C combines both. That means open drain as well as push-pull is required for I3C driver. But in case of I2C, only open drain is required. Open drain driver is required. But in case of SPI, only push-pull is required. But open drain driver comes up with a lot of advantages with address arbitration. That is fundamental advantage of the open drain driver. So, and also it's easy to get the acknowledgement because of the open drain architecture. So this is the fundamental difference between push-pull and open drain. And in case of I3C, we require both push-pull and open drain driver. Okay. Let me go to next slide. Okay. So how you can see here is open drain followed by push-pull. In case of I2C, it's always with a weak pull-up resistor. That is the rising edge and fast falling edge. That's because of course, it has a slew rate control in I2C. So this is also well defined by the I2C. So the limitation is slow rising edge. That's a fundamental limitation of I2C. And you can see here, there is a lot of time it requires to transmit 1 byte of information. Now, when it comes to I3C also has a limitation. That means it has to start with open drain mode. That means first 9 bits of information must be with a slow data rate. You can see here the open drain, it starts with 4 MHz frequency. However, once it receives the acknowledgement, then it can go to high speed. Then immediately the data can be sent at 12.5 MHz frequency. That means initialization is an overhead here for the I3C, but once it picks up, the high speed mode can be enabled. Okay. So that is, you can see here clearly how long it takes for the I2C, whereas in I3C, you can really communicate very well within a short duration of time. Okay. So you can see here, that means the driver of the I3C must support open drain driver in this case. After that, the driver must change to push-pull driver, right? That means the driver must be capable of supporting both open drain and push-pull. But in case of I2C, it's not the case. Should be only the OpenTrine driver. Okay. Let me go to the next slide. So these are some important functions of I3C communication. So write operation, you can see it starts with a OpenTrine mode, and it goes to the high frequency mode, and it can communicate during write operation. So I won't focus much on this. This is just a write operation going from controller to target. Then read operation. So in case of read operation, first it starts with a OpenTrine, and then there is a command to read the data. After that,
excuse me, sir.
Yeah.
Sir, PPT is not visible, please.
PPT is not visible. No?
Not visible.
Oh. Come. Why it is not visible? I think I am not able to share the screen. Only meeting organizers and presenters can share screen.
Sir, your ID, Geeta, wait, sir.
a.geetanath@gmail.com.
Wait, sir.
Maybe can I leave the room and then you can join again?
Sir, we make you as presenter, sir. Now you can do.
Yeah, correct.
You can do, sir.
Okay.
Now it's come, sir.
Now it's coming, right? Okay.
All right.
Visible, sir.
Yeah, nice. Okay, so the read operation, I3C, it can read the data here using these commands. That means slowly it should start in the broadcast mode, and then it has to implement the CCC, that is the command code, and then read operation, it can get the data. After that, HDR DDR mode, this is the high definition data rate. This is where you can carefully see here, observe here. These are the SDR mode. That means the data is only on the one edge, maybe on the falling edge here. But here you see here the data can change on the rising edge as well as falling edge. That's the reason it becomes double data rate for HDR DDR. So data rate effectively can be doubled. However, it has an overhead. That means each data comes up with 2-bit preamble, 2-bit parity bits. Let's assume there is a 16 bits of information. However, it requires 20 bits of information to communicate the HDR data. Okay? That's the overhead. So this is the HDR DDR mode. Now I would like to focus on what is static addressing. You can see the examples of I2C slaves. There are so many slaves in the industry, in the market. So temperature sensors, this is only sensors, memory devices, display drivers, I/O expanders, RTCs, audio codecs, power management, communication modules, CC camera controllers. Like that, there are so many devices available in the market. Okay. However, from I2C, only there is 7-bit address, right? That means if someone wants to propose a new product in the market, they need an address, and they have to choose one of the 128 available address in the I2C according to I2C definition. That means it's highly possible that one of the slave address can conflict with other slave address. Okay, so because of so many devices in the market, 2 slaves can have a unique address. Let me show you in the next example. One example is you can also search in the internet. The temperature and humidity sensor address is 0x76, and also RTC real-time clock module also having 0x76. When both devices are existing on the I2C bus, what is the problem here is when master sends an address 0x76, this device slave 1 responds as well as slave 3 also responds. Both will send an acknowledgement, which is a conflict. That means both wants to drive the data, which is not correct. So we face an issue with data communication. That means on the I2C bus, fundamentally, no 2 slaves should not have the same address. 2 slaves should have different address. Then only the successful communication can happen. Okay, this is called address conflict. So both devices cannot exist on the bus. There is an address conflict here. Okay, there is the communication error. Is it clear? This is an important feature. Then what I3C proposed is dynamic addressing. What does it mean by dynamic addressing? Still, I3C devices can have the same static address. Let's assume temperature sensor and humidity sensor, but both are I3C target, not I2C target. They comes up with same static address. However, what it does is I3C does is it tries to get the information from each target. Okay. In the previous case, the information, the static address is defined by the manufacturer. Let us assume NXP makes the temperature sensor and analog device make the RTC module. And NXP defines one address here, analog device defines the same address here. Okay, that is already pre-built inside the each slave in I2C. But in case of I3C extended a capability called PID. That's called 48-bit PID. This 48-bit PID, how they described it as 48-bit PID. Let me go to next slide. This 48-bit PID that is defined based on the manufacturer information. That means NXperia has one unique code. NXP has another unique code. TI has another unique code. Like that, each manufacturer has their own unique code. On top of that, the DCR register that provide, you see here, if there is both parts are from the same manufacturer. Let's assume both temperature sensor and RTC are from the same manufacturer. Let's assume analog device manufacturer temperature sensor and RTC. However, because of their functionality difference, it is possible to have different DCR values for the two I3C targets. That means using 8 bytes of information, each and every target on the I3C bus can be distinguished. So what it does is, first I3C controller initiates a ENT-DAA procedure, enter dynamic addressing procedure. So I3C controller initiates this communication. Then it reads the 64-bit information, 8 bytes of information from each and every target. Let's assume first target 1 shares the information back to the controller. Controller records the information of I3C target 1. After that, I3C target 2 shares the information to I3C controller. Then I3C controller records the information about I3C target 2. So then what happens is, I'll go to the next slide. Let's assume here in the same slide I have put it here. First it starts with ENT-DAA, then 48-bit PID. There is another 8-bit BCR, 8-bit DCR, total 64 bits is coming from the target 1. Then I3C controller records this value. Then I3C controller issues a dynamic address for target 1. After that, I3C controller reads the 48, again, the information from I3C target 2. Then it issues another dynamic address to target 2. In the previous slide, we have an address conflict. That means I3C target, I2C target 1 and I2C target 2 having same address. Now using I3C protocol, they get different addresses. So this has one address, this has another address. So address conflict is resolved here. So this is one of the best feature in I3C. That means effectively many slaves having same address can be possible to attach to the I3C bus. That's the fundamental advantage. Okay, any questions here? I hope it's clear for everyone, but I'll share the slides. Later you can also go through the slides. Okay. Okay. Then let me go to the next slide. Advantage of IBI, in-band interrupt. Okay. So I will explain through one of the NXperia product. This is a 9555 GPIO expander. It is a serial to parallel conversion. That means we get that this is master controller. Master shares the data serially 16-bit information. All the 16 bits are sent to parallelly to the 16 IO ports. Let's assume there is 2 bytes of information that is converted to parallelly, and it goes to different IO ports here. Okay. However, let's assume the temperature sensor wants to say that, okay, I have a new temperature reading. Please read back. Please read back. How can it inform using I2C line? Using I2C line, it is not possible. That's the reason interrupt is introduced here. There is another pin and another line using which any parallel port can communicate back saying that there is a information available on one of the P port. Please read back the data. Okay. So the interrupt can be this port or this port or the last port. Any port can generate an interrupt here. Once the interrupt is generated, then master controller initiates a read operation, and then it reads the data of all the parallel port onto the controller. Now it's an extra pin in the system. Interrupt is an extra pin. Okay, that's a drawback. That means always when we go with any mobile application, engineers look for less number of pins. So this is a overhead to the microcontroller. What I3C does is it has an in-band interrupt. That means I3C can generate an interrupt on the SDA line. So let's assume there is you can imagine the similar system, 16-bit IO here. One of the temperature sensor wants to request a readback. Then the I3C target generates an IBI, and it generates IBI on the SDA line. After that, I3C controller knows that, okay, there is a IBI in-band interrupt is coming. Let me see which one is asking for readback. It also has the capability that it not only gives an interrupt, and it also says that which channel is requesting. In the earlier case, the controller doesn't know which channel is requesting. It can be this channel or this channel or this channel. Anyone can generate an interrupt. But in this case, there is a possibility that I3C target can say that, okay, the temperature sensor is requesting interrupt. Please read only the temperature sensor. So that's the advantage of in-band interrupt. It integrates interrupt functionality as well as information about which channel or extra information. So you can see the comparison here, I2C. So it requires a extra signal to inform master, but MIPI I3C doesn't require any extra signal. And also MIPI I3C integrate its ability to send the information with type of interrupt also. Okay. Next one, this is the advantage of IBI. Let me go to the next slide, then I can ask for questions. So in case of in-band interrupt, how it works is, let's assume there are 2 targets, I3C target 1 and target 2. If both wants to send an interrupt, right? Let's assume there is an interrupt coming here and also interrupt is coming here. How does it resolve the address conflict? That means this target 1 tries to send a address. This is also tries to send an address. Then it's a wired under operation. What will happen is the one which has the lowest address that will win the race. In this case, let's assume address of target 1 is 0101110. The assume address of the next target is 0101010. In this case, this is the lowest address, right? So this is a wide and operation. So target 2 wins the race. That means controller knows that target 2 is requesting interrupt, and target 2 wins the bus. After that, I3C controller initiates communication from I3C target 2. That means it reads back the data from I3C target 2. So that's called in-band interrupt. So there is a clear procedure developed by MIPI I3C. That means this in-band interrupt is a very, very useful feature. Okay, any question here on the in-band interrupt?
Sir, no questions from participants, please.
Okay, that's good. But I would encourage really go through the protocol and see what is the really useful feature of this in-band interrupt. It's an interesting application. Next one. Then hard join. What does it mean by hard join? There are two cases of hard join. One is, let's assume in server application, someone wants to, in backplane application, someone wants to introduce a card dynamically. Let's assume the server is running and someone wants to introduce a PCI card. Then what will happen is it requires a power cycling or proper protocol. But in case of I3C application, if server is using I3C application, then it can easily recognize the one which is joining on the bus. It doesn't need to power down and power up. So dynamic joining of the I3C target is possible. That's one case. That means if target N is physically inserted on the bus. Second case is if the target N is already mounted on the board, but it is powered off. Let's assume in one of the application, if this one is, let's assume our mobile application, thus we wanted to turn off the screen. So we switch off the screen power, and if the screen power is activated, immediately the screen will join on the bus without any interruption. So in that case also, this is very much useful. That means this particular I3C target can be powered down and power up. Okay. In both cases, hard join is really a useful feature. However, I3C has a really good recommendation here how hard join can be possible. So what it does is the target which wants to join hard join, it generates a address 02, okay, on the bus. If 02 is generated, this is a reserved address by the MIPI I3C. Then I3C controller knows that, okay, some device is joined on the bus. Then it will allocate a dynamic address for this target. That means I3C controller, again, it starts the dynamic address allocation procedure, like I explained in the previous slide. And what it does is it reads the information from this target, that's 48-bit PID and BCR and DCR register, total 64 bits. It reads back from target N. Once it reads back from target N, it records that target N value inside the controller, and then the I3C controller assigns a address to this target N. So hard join, once it is hard join, it will get a new address. Okay, then let's assume there is a device which is added. However, there is already communication happening. Let's assume I3C is communicating with the camera. I3C controller is communicating with camera, and suddenly some device is joined. Then first scenario is, then immediately I3C target N, what it can do is immediately it can initiate a hard join request. Sorry, this case hard join request. However, the controller sees that it is in between some transaction. It doesn't want to accept it. Then controller says that, okay, I don't want to accept it. It generates a no acknowledgement. That is scenario 2. Okay. In the scenario 1, if the target, if the controller generates an acknowledgement, then the hard join is successful. That means the device is successfully joined the bus, and then target N receives a new address with a NTDAA procedure. But in case of scenario 2, the hard join is not successful. Then what happens is, after some time, the target again tries to initiate the hard join procedure. That means it waits for a long time. Again, it generates a address 010. Then, 02 is the address. And then the controller tries to assign the address after some time. Okay. In both scenarios, the MIPI I3C has a clear direction, and then the newly added device should be successfully joined. Okay, that is hard join. Okay, so you see here the hard join procedure. First, I3C target N generates a 7H02, that is the hard join address. Then I3C controller generates NTDAA procedure. After that, I3C target 10 shares the information about its own information, which is the manufacturer, what is the type of the device, that's PID. And after that, it receives the dynamic address. So it follows 4 steps procedure. Once it gets the dynamic address, then it can successfully initiate the communication with target N. That's the hard join procedure. Okay. Next question. I have a question. Let's assume there is a hard join happened. At the same time, there is an IBI request from I3C target 1. There is a hard join request from I3C target N. Which one will win the race? Anyone can answer. Which one will win the arbitration? You understand? So both follow the same procedure. The I3C IBI shares its own address. In case of hard join, it tries to share 02 address 02. But which one can win in this case? Either this one can win, or this one can win, or Y, one of them can win the race. Okay, please think about it. But the answer is the hard join one will win the race because this is the lowest address. It's a 02. So all the other I3C targets will have higher address. Higher address will never win the race because of the wired and operation. So like I said in the earlier case, let me show you here. Here, the same thing what I try to explain here. The address for the I3C target 1, target 2, they are at higher in nature. So the one which has the lowest address that win the race. In this case, the hard join has the lowest address, which is 02. So the hard join will win the race, and the hard join request should be accepted. Okay. So this is an interesting thing to understand what's the difference between I3C and IBI and hard join mechanism. Let me go to next slide. Okay, CCC. So common command code. These are the different command codes defined by MIPI inside I3C protocol. They are classified as broadcast CCC. That means it kind of broadcast message. Every slave receives the message. And direct CCCs, those are specifically to one of the target. So there are so many commands available. If someone is interested, please go through this. These are the features. Using these features, I3C communication is started. Then HDR DDR. This is the high data rate, double data rate. It comes up with a different procedure. So you see here, first it starts with SDR, and then there is a special CCC that's called ENT HDR. After that, high data rate is started. So once the high data rate is started, then the data can be transmitted on both edges. So you can see here on the rising edge as well as falling edge, the data is getting transmitted. Okay. So this is one of the feature to extend the data rate of I3C. Then error detection and recovery method. So there are several methods defined here. I don't want to go through this one. So what are the challenges inside the with I3C? That's the one of the thing I really wanted to discuss. Okay, basically, controller generates a clock and it gets the data, right? So it generates the clock, and then the clock is taken by the target device, and target device process the clock and it generates the data. So there is a round trip delay. That means the controller generates a falling edge, and before the rising edge of the next rising edge, it needs to receive the data back. So you can see here, this is the push-pull mode where the clock is generating falling edge, and the data should be available before the next rising edge. So there is a round trip delay involved here, and the round trip delay is very important for the successful communication. So this 32 nanosecond that is defined, that is what I remember, is important for the round trip delay. That means there should be several factors should be accounted: pad delay and digital delay and the output push-pull driver delay. So this is a really challenging with respect to timing in I3C. So this is a real-time challenge. That means that when we try to implement the target at 0.8 volt VCC or 0.9 volt VCC, meeting this requirement is very, very challenging. Okay, this is something what I found out in my project. Then electric characteristics of open drain mode. In case of open drain mode, like you see, its low period is 200 nanosecond. And also high period also 200 nanosecond. So this is better than I2C proposal. And there are several timing parameters defined by the I3C here. Okay. And then push-pull mode. In case of push-pull mode, like I said, the clock frequency maximum 12.5. However, it can also go to 12.9. There is a margin allowed by the I3C. Then clock period, low period, that should be either 24 nanosecond at the interface, and clock high period, that's 24 nanosecond, that's also at the interface. Then important things are 12 nanosecond, that is important thing. This rise time, fall time, that's also around 12 nanosecond. There are also, one of the thing was, you can see here capacitive load per bus line. So this is 50 picofarad. So this is the fundamental limitation of the I3C. In case of I2C, the capacitance can go as high as 400 picofarad. So, but in case of I3C, because of the push-pull driver, so 50 picofarad is a major limitation of the I3C protocol. However, it's not completely limiting. The customers can overrule this and can extend this bus capacitance. So at low voltages, there is also another proposal. It can extend up to 100 picofarad. Okay. Any questions here on the open drain and push-pull?
Sir, here there is a question, sir, from one of the participants.
Yeah.
Sir, you are told that I3C is benefit to identify the which sensor are requested.
Yeah.
My question is that is it identifies only single request or multiple requests at a time?
Okay, it only accepts a single request. However, it will prioritize. Let's assume the camera module is requesting and the temperature sensor is also requesting. Then what target does is it prioritizes which one is highest priority. Let's assume the target thinks that the camera module has the highest priority. First, it prioritizes the camera and it generates the IBI for this camera target. After that, it sends the IBI for the temperature sensor.
Okay, sir. Carry on, sir.
Okay, is it clear?
Okay,
good. Let me go to the next slide. Okay, so the limitations of I3C. Fundamentally, like I said, I2C can go to up to 550 picofarad for FM plus. In MIPI I3C, it can go up to 50 picofarad. However, for low voltage application, it can go to 100 picofarad also. And industry adoption, right now, it's very heavy. That means so many products are there in the market. Right now, it's slow. So we need to wait and see how it will pick up. But we have a huge hope that it will pick up very soon. Then improvements, there are no improvements for I2C. However, MIPI I3C is planning to release one more protocol version very soon. Okay. These are the limitations of the I3C in comparison. Okay, so I would like to share some information about this protocol. Let me see. And then we can go to question and answers. Okay. So you can also request for protocol from MIPI Alliance on the I3C basic specification. This is open for everybody. That means it's a public version. However, you cannot download directly. You have to request through maybe from your organization or university. Then you can get it the specification. It takes a lot of time to understand this protocol. However, if someone wants to develop a target, it's possible to develop the target functionality on the FPGA, and you can buy a controller from NXP or TI, and the target can interact with the controller. So it's a good project for students to start with I3C target to understand some of the features. At the same time, many companies offer IP also as a dedicated IP. Then it's also possible to program on the FPGA any I3C target. They're not that expensive also, around 50K or 60K. Anyone can buy the I3C IP. So let me see. So this protocol starts with some of the basic things, and then it speak about the protocol, the SDR, single data rate. Let me see. Single data rate and how the bus communication happens. Like I said, there are registers, dedicated register for each controller and target, BCR, DCR, 48-bit PID. So it speaks about this. Then I3C, then coming to the bus conditions, bus availability condition. This is also very, very important for hot join and IBI because hot join and IBI cannot be requested whenever target want. It has to look for the free bus. Then only hot join and IBI can work. It also speaks about dynamic address assigning mode, like I said, and then hot join mechanism, in-band interrupt. Then I3C bus with multiple controls, handoffs. It's also it talks. Then timing control. This is also important thing, but we never explored this. CCC. These are the CCCs which are main features of I3C. You can see there are several commands here where I2C doesn't have any commands. So using these commands, I3C can I3C target can interact with with I3C. I3C controller can interact with I3C targets. So these are also really important. One of the things that I explained was NDAA, Enter Dynamic Addressing Assigning Mode. Excuse me. So this is what I have explained, how the dynamic address is assigned. Then coming to the target reset, I said to you that if there is a bus stuck happens, then target reset is a helpful feature. And also I spoke about high data rate mode. That means it's possible to extend the data rate to double. In case of I2C, it's not at all possible. It's only single data rate. So high data HDR also we discussed. Then multi-lane data support. That means it's multiple data lanes also possible on the I3C bus. After that, I3C electrical specification, DC. I explained some of the basic timing specification, open drain and push pull. Yeah, this is a good one. Okay. So someone asked me, can you share the book title? I think it's not a book, it's a protocol. So it's called MIPI I3C Basic Specification, version 1.1. So you can request in the MIPI website. We'll show you how to request also. PDF.
Any
So
questions
if you-
from participants?
Yeah.
Yes, sir. One small question.
Mhm.
Sir, what's I3C supports data rate, sir?
Maximum 25 Mbps, 25 megabits per second. Using
25
HDR
megabits.
DDR mode. Using SDR mode, it's 12.5 Mbps.
Okay, thank you, sir. Thank you.
Yeah, you can request this one public version. Yeah, I think this cannot be requested, but the public version can be requested. We'll send you this link also. Okay. Yeah, I have to stop in 5 minutes, but I'm open for any questions for 5 minutes.
Sir, one participant asked one question. Said the book title and other name about that I3C supports data rates.
What I3C supports data rate? This is not a book. I told you, right? This is not a book. This is a specification.
Yes.
I think there are no books available, at least as far as I see. It's only the specification, protocol specification we refer to. Yeah.
Please, any questions from participants?
One more question. What's the special features for Sir, what's the special features for I3C than I2C?
In-band interrupt, dynamic address assignment, hot join. These are the 3 important features. That's what I said, right? So if you see my presentation, I can also show once again. I compared the features of I3C in one of the slide. So you see here, IBI no capability for I2C, hot join no capability, and there are also no CCC, no built-in command for I2C. Then static address, the dynamic address is not available. Yeah.
Is it support to Spartan 3?
I think so. Spartan 3 is FPGA, right?
Yes.
Yeah, I think so. It's perfectly fine because we did program in not Spartan 3. I think we did the programming on Altera. I think one of the FPGA we bought it. Yeah, it's not in the gigahertz, right? It's still in the megahertz. So the modern FPGA should support. Yeah, it's not a problem. But only thing is whether the drivers can support, we don't know because it has to change from push-pull and open train. So you see here, I3C requires both push-pull and open train. So that is something a bit tricky. So we need to see how that can be implemented. Okay.
Sir, is it low power consumption?
Is it? Sorry.
Is it low power consumption?
Yeah, it's low power consumption. At least in once it goes to push-pull mode, it is low power consumption. That means what happens here is for open train, you require a pull-up resistor, right?
Yes, sir.
What the controller does is controller has inbuilt pull-up resistor, and controller disables the pull-up resistor when it goes to push-pull mode. That's how the power consumption is saved here. So, but when it is open train mode, still it relies on the pull-up resistor. Once it goes to push-pull mode, then the pull-up resistor is completely disabled. Yes, it's a low power consumption. Correct.
Thank you.
Okay.
Excuse me, sir.
So, yeah.
Sir, good evening, sir. Myself, Venkat Lakshmi. Sir, your overall presentation is nice, sir. Very good explanation. So, and my doubt is hot joint hot joint slide I saw, sir. Hot joint slide. Can you open that slide, sir, once again?
Sure.
In that target 1 and target 2 is there, sir. Correct. And number of targets also is there. So already you asked that question. So the first address is there in a target 1. So reach the address, the first target 1. So, but my doubt is two targets given to the same bus, that is nothing but the same line. At the same time, input is also given that both target 1 and target 2. So, only target can depend upon the address, sir. First, it's taken to the first higher address. That's why, sir. Or not?
Yeah, let's assume simple thing. Let's assume target 1 has P. Sorry, I'll just represent in very long way. 0 0 and 0 0 0. Okay, let's assume target 1 has this address. Okay, and target 2 has something like this.
We given same timing, sir. Same timing at a time given to the target 1 and target 2, sir.
No. It happens in a different time. So basically, dynamic addressing assignment. So they get the address in, let's assume I'll show dynamic address assignment, right? So first, let me show here. First, this one gets the address. After that, target 2 gets the address. Okay. So they get in different times. They get the dynamic address at 2 different times. However, they keep the address. Once they get the address, that address will stay as long as the power cycle is power is available. Now my question was, let me put the same thing here. Let's assume target 1 wants to generate a IBI. Okay, it's going to write this address, right? In target N, it doesn't have any address yet because it just joined. It only generates a address 02. Okay, so hot join address is something B 0 0 0 0 0 0. Okay, so when both tries to write the address at the same time, so only the hot join will win because this is the lowest, right? This one is the highest.
Okay, so only higher order address bit, and just that's it.
Okay.
Okay, thank you.
Okay. Yeah, no problem. I have a hard stop here. If anybody has questions, I will include my email in the presentation and I'll send it to Shivasangari. And then, yeah, if you have any questions, feel free to ask me. It's okay, Shivasangari?
Yes, sir. So thank you very much for this session, sir. It was a very, very wonderful session.
No problem. Okay. If you have any, if you need any help for the projects or anything, you can also, yeah, always I can be helpful.
Definitely we will contact you, sir. Sure, sir.
Okay, thank you. Thanks everyone for joining.
One second, sir. Now I request Dr. Nokura, sir, to conclude the session.
Okay, madam. Thank you. Sir, I am very happy to say my opinion about our session in this session. On behalf of our GMRIT EC department, I extend very gratitude to Mr. J. Geetanath, Circuit Design Architect, for his insightful and enriching session on transforming from I2C to I3C, and your expertise and depth of knowledge have provided us with valuable insights into this crucial domain, bridging theory and practice flawlessly for research students. We deeply appreciate the time and effort you took for explaining complex concepts with clarity and practical examples, making this session highly engaging and relevant. Your discussion is very important for researchers. And I also thank that our participants that asking very enthusiastically to ask the questions and clarify their doubts. Now, let us take forward that knowledge gained today and apply it meaningfully in our work, studies, and research. Once again, thank you, Mr. Geetanath, for sharing your valuable time and expertise with us. Thank you, sir. Thank you very much, sir.
Yeah,
and have a great day.
Yeah. Have a nice evening.
Thank you.
Okay.
All right, sir. Thank you.
Bye.
Bye.
Thank you, sir. Thank you, sir.
Thank you. No problem. Bye.
Thank you, sir.
Vase garu. Hello.
Yeah, ma'am.
Sir, shall we start the next session? Manikanda sir has joined.
Just now he joined. 1 minute, ma'am. I will call once again.
Good evening, sir. Manikanda sir. So Manikanda sir has joined.
Ma'am, coming, ma'am. 1 minute.
Hello.
No, he has joined. He has joined.
Yeah,
Yes,
yeah.
sir. Good evening, sir.
Yeah.
Yeah, good evening, Andy.
Yeah. We are once again welcome you for the second session, sir.
Yeah,
On
thank
the
you,
day
ma'am.
4. Yes.
Thank you.
Revati ma'am,
Can
you
I
can
share my
start.
screen? Yeah. Can I share my screen?
Okay, ma'am.
Yeah, sure. Yeah.
Good evening, sir. Good evening to
Andy.
all. It's my pleasure to introduce today's resource person, Mr. C.H. Manikanta. Mr. Manikanta currently working as a senior physical design engineer at Moss-Chip Technologies with 6 years of experience in the VLSI industry. He has a strong background in physical design. His area of expertise include VLSI physical design flow. This includes floor planning, placement, routing, and timing closure, which are crucial for ensuring the performance and reliability of integrated circuits. He worked on multiple projects in the VLSI domain, collaborating with cross-functional teams to meet design specifications and timelines. He is passionate about advancing in his career in physical design, staying updated with the latest industry trends and tools. His goal is to contribute to cutting-edge technologies in semiconductor design and play a role in the development of innovative solutions in the industry. Now, I would like to welcome Mr. Manikanta sir and request to take over the session. Thank you, sir.
Yeah, thank you, ma'am. Is it visible, Andy?
Yes, sir.
Yeah. Today I'm going to explain about what is routing. These are the points what I explained. We are talking about the PNR in the earlier session. So when you come to the PNR, the routing is the crucial. In every stage we are using the routing. So now I am explaining about what is routing and also what is metal layers and what is via stack and also how these metal layers are connected. These are through track assignment and also what are the algorithms existed in the VLSI and in ASIC flow how they are using. Okay, I am explaining about these things. Yeah. Coming to the routing, routing is nothing but in our ASIC we are simply defined as the process of creating physical connections using metal layers. Like if you consider a road, there are so many vehicles are passing on the road. So if you consider there are two roads dividing through divider, that is 2 lane. If there are 4 lanes, 6 lane road, like that also, we are traveling from one source to destination by using the road. Here also, the routing is done through vias and also stacks. And also, if you consider this is one layer, there will be horizontal and vertical layers. This is a horizontal layer and this is vertical layer. Okay, so this is one via. Via is nothing but it is the interconnection between top to bottom layers. Okay, so and also these are the tracks. So what is nothing but track assignment is nothing but the to travel the route, there will be some particular route should be adjusted. That is nothing but the track. By using the tracks, we are doing the routing. Okay. So here there will be so many tracks, horizontal tracks and also vertical tracks. So what are the horizontal tracks and what are the vertical tracks? I will explain. So we are talking about the multiple layers. Like so, if I consider M4 layers, so how the employee layers adjusted? There will be one ML layer. After that, there is one VR. From VR2, there will be one metal 2. From VR metal 2 and metal 3, there is one VR. from metal 3 to metal 4, there is one via. Like that, the vias are stacked in manner by connecting from top to bottom. So this is the nothing but via stack. If I need more layer, so this metal will be extended to here like this. So if this is metal 1, this is metal 2. So this is extended from here to here. And also there will be pitch and spacing also should be adjusted. The pitch is nothing but the distance between the two tracks. If I consider these are the vertical, in some technology, the horizontal layers are adjusted and vertical layers are adjusted. Some horizontal layers are odd numbers, some vertical layers are even numbers. In other technologies, some horizontal layers are even and some horizontal are odd. Like that, technology they may vary. So it is dependent on the foundry. So if I consider here, M1 is the horizontal. So metal 1 is adjusted here, and also some other metal, if any metal is metal 1 is adjusted, it is also from here. So from metal 1 to this track to this track, we are calling this as tracks. So from this track to this track, we are calling it as metal pitch. This is metal 1 pitch. If you see, this is metal 2. This is metal 2 pitch. So how these metals are connected to our standard cells? If you see this here, we are placing the standard cells like I explained in the earlier session. So the standard cells have their pins. So those pins are in M1 or M2 or M3 layers. So the M1 and M2, M3 layers are connected from top layers to these layers using vias. As I said in the earlier stage, there will be follow pins. The follow pins are in M0. Through M0, they are connected to the M1, M1 to M2, M3 to M4. Like that, they are connected to the top layers. So through follow pins, we're getting only power. There will be no data, only power we are getting through these M0 layers. From metal 1 to other layers, we are using for signal layers. Why can't we use the M0 for signals? Why? Because the M0 is common for all the cells. If you place the standard cells here, the M0 is going to this standard cell, this standard cell, this standard cell. So the M0 is you are using in every way. So if you use M0 for also data signal layers also, it will be more difficult. There will be congestion. So that's why we are not using the M0 layers for data layers. And also for signal connection, pin connection, we are using either M0 or M1. The pin connection is very minute. If you consider this is standard cell pin, for this you can use M0, but not enter the tracks. So this is the routing. By using this routing, we are going to the later stages. As I said, track assignment. Okay. What are the routing algorithms? Okay. Before that, going to the routing, what I said is the metals, right? So in metals, there will be stacks like M12, there will be M14 or M15. As an example, I kept only for M4, but in real time, what we are using till M15 layers also. So in this M15, how the layers are varying. The M0 is some other pitch, some spacing. The from M1 to M2, some spacing. From M3 to M5, some spacing. And also from M6 to M10, some spacing. Like that, they're following. And also the width is also varying from M0 to top layers. Why the width is varying? Okay. Actually, for any standard cells, what we said, there will be clock and there will be power also, and there is also signal routes. So if you use all the layers for signals, there will be no issue. There will be issue for power. Why? The power is going to all the routes, all the standard cells. That's why we are using the higher layers for power, like top layers. Why the top layers? The top layers are having the more width and also more spacing. If you consider one width here, one width is going, this is the width. If this is one width, there will be spacing from here to here. We are using the one spacing. Why? Because uh, I will explain the why are using the more spacing instead of one spacing. Why can't we route here to here? I will explain later. So in top layers, the width is more. As you know, there is the more resistance. There is the more resistance drop. That's why what you are using to decrease the resistance, we are increasing the width. The length is constant but depend on the net length. The thickness of the metal is constant, but what is varying? The width is varying. You know, R is equal to rho L by A is width into thickness. So if you increase the width, the resistance is decreasing. If the resistance is decreasing, automatically the delay is decreasing. That's why we are using the more width layers for higher layers. Then we can ask, why can't we use the more top layers for signals and clock nets also? Yes, we can use, but if you use more width layers, the total design is only net dominant. If the net is net dominant, you can't accommodate all the nets, you can't accommodate all the cells in the design. That's why we are using, particularly for power, we are using top layers, and also for signal nets, we are using the bottom layers, and for clock, we are using the medium levels. Why we are using the medium layers for clock routing? Clock is also more compared to power. After the power, the clock is the high frequency signal. It is going to the every route. That's why we are using the clock as the middle routes. If you use the clock also higher layers, it will be difficult. So that's why it is medium layers. And for signal layers, we are using from lower layers to the top layers. Okay, so this is the what I call as routing and VS stack. Okay, let us come to the algorithms. Mainly, the routing is divided into the two stages. One is global routing and another is detailed routing. What we do in the global routing and what we do in the detailed routing, and also the global routing is of two types: line routing and maze routing. The detailed routing is of two types: channel routing and switchbox routing. Okay, these are the routing algorithms for our every design we are using. In which design, in which stage we are using global routing, in which stage we are using detailed routing, I will explain. So before going that single layer routing or line routing, what is this? So if we consider 2 points here, let us consider this is source, this is the target. So in single layer routing, the wires do not cross. It is continuous planar region. So if we consider the routing is started from here to here, there is only single routing adjusted. This is nothing but the straight type river routing. So the river, always it is flowing, it is straight river type. So if you see this is one single layer, this is one single layer, this is one, but this is not entire single layers. So with this only, if it is okay, then why can't we go for other routings? Okay, so if there will be any zigzag connection, then the single layer routing is not possible. So we are using single layer routing for particular applications, like in the initial days. After that, the single layer routing is converted to the maze routing. In this maze routing, what you are doing? In the maze routing is nothing but we are operating on the uniform rectangular gridded area. Let us consider this is the source, this is the target. Let us, I am connecting these transistors through these routes. So what this algorithm will do is, this is nothing but it will maintain certain incremental spacing. So the spacing from here to here same, from here to here same. If I consider this is one track, this is one track, this is one track, it will not travel like this. Why? Because this should follow minimum spacing, and also from here to here, this should follow minimum spacing. That's why it will follow from source to target through zigzag manner. Like this is maze routing. So if I represent, this is the connection, this is not representation. Okay, this is okay. So why, if it is okay, then why you are going for the higher routing layers, higher routing algorithms? Why? Why? Because actually this is a planar rectangular grid graph. So the in this you are using the blocked vertices. So you are blocking here. You can't use this tracks. So that is the drawback of maze routing. By using this lane routing and maze routing, we are going to the next stage. This comes under the global routing. If you consider the detailed routing, these are two types I said: channel routing and also one is the switchbox routing. So in the channel routing, what we are doing is the algorithm what is doing is one of the most important. So if we consider this is one channel, this is one channel, this is one channel, and also this is plus type. We are forming as plus, and also this is T type. So in the channel routing, we are using the wire routing of large integrated circuits. For every ICs, we are using the channel routing. So okay, in the channel route is nothing but if we see two parallel connection, I will show the box here. Yeah, if we see channel, if we see this is one edge, this is one edge. From source to destination, there will be only two edges. In between two edges, what is the routing is happening? That is channel routing. From here to here, it is from here to here channel. From here to here, it is channel. But it can't go to the other side. From within two edges only, the channel routing is working. Okay. So after that, switchbox routing. So in the switchbox routing algorithm, what we are doing is, if you consider when four channels meet a cross connection, let us see, this is A. In this A, this is 1, 2, 3. There is no conflict. By using channel routing, you can design the routing, right? By using algorithm, This is one channel, this is one channel, this is one channel. It's okay. If you see here, this is conflicted channels. What happened here? 1, 2, 3, 4. If you go from 1 to 2, there will be L shape is needed. So if you consider channel, this is one channel, this is one channel. But here the junction, what it is formed as, we are calling as switch box. At that switch box, the channel routing is not possible. So to overcome this type of routing, we are coming to the switch box routing. If you see 1 to T, there is a square shape connection. This square shape connection is formed by switch box. So in the switch box, there is four sides. So if you see, this is 1, this is 2, this is 3, and this is 4. From this edge to this edge, from this edge to this edge, from every edge to any edge, we can do routing. So this is one of the routing algorithm. If you see, if you consider the channel, this is one channel, this is one channel. So you can ask, the maze is also working like this. Then what is the difference between that and this? Yes, the maze routing is nothing but it will connect only uniform blocks. If you see this edge and this edge should be same. So it is an uniform rectangular gridded area. The gridded area should be uniform. But in our switchbox routing, there will be no uniform. So it may be less, it may be high, but it is considered as one channel. This is considered as one channel. This is considered as one channel. This is considered as one switch box. So like this, channels and switch boxes are adjusted. By basing on this, we can do routing. All these all comes under routing algorithms. Then in ASIC, how can you use these algorithms? So the first step in PNI is nothing but already I said earlier, the placement of cells. So let us recap. You know that in basic, there will be synthesis. Synthesis is nothing but converting RTL code to gate level netlist. In placement, what we are doing, we are placing the standard cells. So there will be logical connections. There will be no special routing here. Just it is assuming as the tool. Here, after that clock tree synthesis, after the signal routing, next it is timing closure. I will explain these steps regarding the routing algorithms. Okay. So as you said, the gate arrays, FPGAs. In the FPGA, we are connecting like this. This is one FPGA, this is one, this is one, this is one. So the connection is from here to here, from here to here. Like this, the connection is existed. After FPGA, we are coming to the ASICs. In the ASICs, we are placing standard cells, right? The simple designs. In the simple designs, we are not using any memories. Maybe they don't require any storage element. You know that if we using the memories, there are storage elements. So there will be no storage elements also. If you see counter, there may be if we see the level shifter, there will be storage element. So like that, there will be some applications that may not be any use storing elements. For those cells, we are having only standard cells. This is one of the standard cells. These are going through feed through cells. The feed through is nothing but from one chip to other chip, other module through some cells. There is connection adjusted in our block. So we are calling it as feed through cells. The feed through cells is nothing but the swing from one input to the other input. So this may be standard cells. And another things are full custom. And the full custom, what we do is there is standard cells and also RAMs also. Either custom RAMs, SRAMs, LM macros. All these macros may be adjusted. Here we are placing the macros like this. Okay, in this we can use channel routing and also switchbox routing. So the algorithms will work here. Okay, the basic PNR flow. If it comes to the basic PNR flow, in the placement, what we are using the global routing. Okay, after why we are using global routing, I will explain. In the signal routing, we are using the detailed routing. So the global routing is nothing but it is partitioned into rectangular regions. So to interconnect each net, a sequence of subregions to be used. So if you see in the logical connection, from here one cell, here is one cell, here is one cell, here is one cell. What the tool is assuming is there is no physical connection. Just the tool is assuming, okay, from here to here there will be connection. So it is not assuming, it is not correct routing. So it is assuming it is from this connection, this connection. The assumptions of it takes to the netlist. Through the netlist there is logical connection. So in the placement, the tool is assuming from this source to destination there will be logical connection, and I will route from here to here, like this, from here to here. Okay. So if there is just any connection from here to here, it will also follow from here to here. Then what is the drawback? So in the global routing, it did not check any DRCs, any issue, if any issues existed, it did not check. So in this, the track assignment is following. The track is nothing but for every global route, some tracks are adjusted. So it performs, the tracks are adjusted in the horizontal and vertical partitions. The reroute, what it is doing is, it may be overlapping the ways. So the track assignment replaces all global routes with metal dies. So what I said earlier, so in the global routing, it did not carry any DRC, signal integrity. I will explain what is signal integrity, all these things. So it connects only pins. It did not check anything. And also these violations are fixed in the succeeding stages. By using those, it will do placement. Let us see. This is one cell, this is one cell, and this is one macro. So the placement is nothing but the placing the standard cell in the core boundary in the adjacent in the adjusted locations. So that is what is optimal locations. The optional locations is nothing but if I see one module here in the placement stage, the module will place near to the ports, and this module is talking to the other modules. The router, what will do is, it connects logical connections from here to here. It may be connection if the connection is adjusted. So the placement is doing like this. Once placement is done, it tries the routing based on the it should be having minimum route length, and also it follows this algorithm. What will follows congestion driven algorithm and timing driven algorithm. As I said, congestion driven algorithm, how the congestion is adjusted and how this algorithm work on the congestion. Okay, so if you see here, the total core area is divided into the G cells. We are calling as global cells. This is one cell, this is one cell, this is one cell, this is one cell. In the placement, what it do is, if there is multiple tracks, if in this I have 5 tracks, in this I have 5 tracks. So the tool what will do is, it routes from here to here by using all the tracks. So there will be connections of 6 routes, but I have 5 tracks. So what is the problem? Just I have less tracks, but I have more routes. So in the placement stage, this algorithm what will do is, so I have congestion. What is that congestion? So you have only 5 tracks, but I have 6 routes. So I have deficiency of 1 track. So the congestion is 1%. The GCL of deficiency of 1% in vertical or horizontal. If it is in horizontal, it is horizontal congestion. We call it as horizontal. If it is in vertical direction, we call it as a vertical direction. Like that, what the tool is doing is, so assign all the routes to all the tracks initially. After that, if any tracks are not utilized, it uses these tracks also. So once the tracks are utilized, if there is no connection, if you see this is the standard cells. If there is no connection, there is no placement. So what we'll do is, this is global routing as said. So even there is no place, this in the placement stage, the tool is doing the routing from one route. On the one route, there will be another route. Why it is not physical routing? It is only logical connection. So tool is assuming I can route. There will be no issue. I will go forward with this algorithm. So in the placement, what we'll do is, based on this, it will connect the routes, the standard cells through these routes. So okay, if the connection is just like that, what is the problem? There we see the congestion. So if the congestion existed, how can you overcome? The tool what will do? So in this algorithm, to overcome the congestion, first initially there will be one placement is done. So it places the standard cells earlier. Okay, so once the placement is done, what the tool is done, it do global placement. As I said, by using the available routing tracks, the routing is done through global routing. Once done, okay, everything is done. Once after the placement is done, there is the legalization. So in this algorithm, the legalization is nothing but, so I have one cell, on that cell there is some other cell. So those are combined. So 2 cells are in single place. So that is the problem, right? While doing the connections. So the legalizer, what will do is, in this algorithm, it move the one cell on another cell to the left side or right side, depend on the place. So if one cell is on that cell, this will move to here. This cell move to here. So like that, the cells are moving. So this is legalization. So even after legalization also, we may have congestion. Why? Because there will be maybe no space. So after that, it will do I fan out net synthesis. In the I fan out net synthesis, what we'll do is, this is one cell, it is connecting to the two other cells. So the fan out is 2. So like that, it is simple standard cells. If you see the clock is going to the so many cells, all the flops, all the sequential cells. So the fan out is more. The in the I fan out net synthesis, what we'll do is, it divides the total clock into the multiple cells. It adding some cells, and also by adding the cells, those connections are spreaded. That is nothing but I fan out net synthesis. In the I fan out net synthesis, what we'll do is, so the total fan out is divided into the single normal cells. If it is more 5, if there is a 10 fan out, it will divide the 10 to the 5. Like that, the I fan out net synthesis is done. Okay, once I fan out net synthesis is done, what we'll do? There is the congestion. Okay, so in this congestion, it will do iteration. How the congestion iteration is done? Okay, as I said, one cell is from here to here, then there is no issue. If here is also there will be some cell, the cells are surrounded by these cells, then what is the problem? So this cell is may not move to here. So that is the congestion. So then what will do is the tool, it will move these cells to the this, like this to this end, this to this end, this to this end, this to this end, like this. So then there's some space is created. So after creating the space, the some congestion is maybe decreased. Why? So if the available tracks are 5, if there are 10 routes, so that should be congestion. So by moving this cell to this cell, this algorithm what will do is, it utilizes the minimum spacing. So that is the nothing but decrease in the congestion. One is the like that the congestion is decreased. The other thing is, in this algorithm, even there is congestion. So if the tool is also not perform any well, so what we do is, we are creating the keyboards here. If the keyboard is nothing but the, we are creating the some space this to the cells. So this cell should be have some space. Then I have some tags availability like this. If you see, so this cell may have some keyboard. Keyboard is nothing but some space. So till this, the other cell will not place here. That is the nothing but hard keyboard. We are call it as hard. Hard. There will be hard, soft, and some other keyboards are there. We are using the hard keyboard. Hard keyboard is nothing but the cell is not placed to here. It is with through the this cell is having some hollow. This is one type of the reduction technique we are using to decrease the congestion. And also one other is, we are using now partial blockages. What is this? Some partial blockages, soft blockages we are using. What is partial blockages? Nothing but, as I said, in the placement stage, the total this is converted as a G cell. In the G cell, there will be so many G cells. So it may be 20 microns, 30 microns, 40 microns. So in the placement, the tool may place some other cells in some area. Why? Because actually this is one module and this is one module. To talk with this module, the tool may place some other cells here. So the tool didn't know, I need to talk with this module and this module. It may place here. So there are so many cells over there, we are getting congestion. So at that time, what we are doing is, so we are spreading these cells by using the partial blockages. What the partial blockage will do is, actually, as I said, there are so many cells. The partial blockage did not place all the cells in a single G cell. So if initially there are 10 cells in a G cell, so right now after using the placement blockage of partial blockage, the 10 cells will not place in that area. Those are spread in a G cell. In a particular area, we can use the partial blockage as bin wise. We may use the total. If you use the total as the one placement blockage, the cells may sit over here in the same. That is also a problem. To overcome that also, what we are doing is, we are creating the placement blockages as bin wise. This is one bin. This is one bin. This is one bin. Like that, we will create the bins. In that bins, the cells are spreading in that bin, having less space. So if it is 20 microns, we are creating as 5 microns. So then there will be less number of cells in one bin. So likewise, we are spreading. This is also one of the technique we are using to decrease the congestion. Okay, congestion is done. Everything is done. Once congestion is done, The tool what will do is timing, DRV, and power optimization. So how this algorithm will decrease the timing, as I said. So if there is two models, if this model is talking here, if this is talking to the flops, so the model will do is to decrease the IO time. To talk with the IO ports, the total cells are pulled to the this IO. So then what is the use? The timing will decrease, but there is disadvantage also. What it is, if this is talking to this cell, this is talking to this flop, it may pull from here to here to decrease the timing, but it may be increase. So this algorithm what will do is it will mostly to decrease the timing in optimum manner. From here to here this some space, from here to here this some space. With that also we get the timing. So even after placing like that also there will be timing violation. To work up the timing violations, what we will do is, so we check the timing from here to here. I'll explain how can the timing is doing setup or hold timing in the later slides. So what we do is we can move these cells to this. If there is margin from this to this, we move this cell to here. Then what will the cell distance is, the distance between these will decrease. Then the timing may optimum. So in this optimum location, how the routing algorithm is used. So if you see routing from here to here, it may be more. There will be more resistance and more capacitance. So by moving this cell to this cell, the resistance may decrease, the capacitance may decrease. So like that, we can decrease the delay between these cells. Like that, so we decrease the timing violations. That is nothing but timing. And also DRV. In this DRV, what this algorithm will do is, it the data is nothing but the max transition and max capacitance. The max transition is nothing but from one cell to other cell, there will be from some 0.5 transition. So nothing but we are giving some transition values to the tool. The algorithm what will do is, so if I have given 0.5, if the input from this to this load, it should have some transition. So the tool what will do is, if there is 100 micrometers of net, the tool will place the buffers in between these nets to decrease the DRV, to decrease the transition. So if there is 100 microns of net, if you place the two cells here, then routing is decreased, the resistance and capacitor is decreased, then the delay is decreasing. You can ask, if you place the cells, the cell delay will also count, right? So compared to this transition, the cell delay what we are exhibiting, by placing this cell, we can decrease the less delay, as it is the optimum manner. If you place in optimum manner, we can decrease the delay. So like that, we decrease the transition. And also max capacitance. These are comes under DRV. In that max capacitance, what we do is, so the total capacitance calculated by this cell may be more. Here only I am seeing this two as the example. In real logics, we have million or not million, we have hundreds. So there will be capacitance of more capacitance on this cell. So what we are doing is, we are decreasing the capacitance by splitting the loads. So what is splitting? So if these are the two, so we are placing one buffer here. If it is more high drive strength, this is less drive strength. This is also high drive strength. This is also high drive strength. We are placing some buffer here, and also it is connected to this. Then the total load decrease. The total load is decreased right now to one buffer and this cell. So that's then the capacitance is decreasing. This buffer will drive this cell. Like this, we are decreasing the capacitance. This comes under DRV. The tool optimum to till some manner, but it will not optimum fully. If the tool optimum fully, you don't have any work, right? So that's why the tool optimum till the till it meets the requirements. After that, power optimization. How the power optimization is done? By this algorithm, if it is having the like more IR, if it is having more net, there will be more IR, right? More IR drop. If it decreasing the routing length also, the power dissipation also less. So like that also, it will decrease the power. And also here we are seeing the multi-bit flop conversion. What is this multi-bit flop means? Actually, if we have 2 bits of input data, in the real life, one flop, only 1 bit is falling from one to other. So there is one clock adjusted. If we have 2 data inputs, so in multi-bit, what we are doing is two data inputs simultaneously can work with one clock, that is multi-bit. So we are converting single flop to multi-bit flops. Then when in which condition? If there is no area of constraints. So if there is area constraints, or if you are using this instead of single bit, if you are using multi-bit, it occupies more area. So if there is no area issue, we can convert multi-bit. With that, there will be clock. We can decrease the clock. So instead of two clocks, we are using only one clock. With that, if you are using less clock, you can decrease the power. So like that, we are using the multi-bit clock conversion. And in the final step in placement is quick intentional routing. As I said, it should not do real route. From here to here, it will assume there will be connection. It is logical connection. So the tool is doing from here to here. So I will assume from here to here there is logical connection. So quickly do routing. After this routing, we are getting the placement netlist. So when this placement is done, this netlist goes to the DFT engineer. So in the DFT engineer, how the algorithm will work? In the DFT engineer, it will test, as I said in earlier session, the DFT engineer will test through ATPC or NBIST logics. So after done, there will be scan stitching. The scan stitching is nothing but from here to here through flops, there will be scan shift register mode. So with that, there will be stitching. So once you get that netlist in the placement, we are creating the scan inputs and scan output regarding DFT inputs. So from there to here, there will be connection like that. So once initial routing is done, we will do these steps. So time congestion is done, timing is done. So if there is no issue, then it is okay. If there is issue, we will inform to the top level. So and also if any levels of logical is also more, then we will inform to the top level. Then it will be decreased. So in placement stage, this algorithm works like this. This is nothing but a global routing algorithm. Now let us come to the CTS. In CTS, what we'll do is CTS is nothing but the process of systematic building of clock tree. As I said, clock is the crucial in CTS. In the entire PNR, if you design the clock good, then it is good design. So for all the sequential elements in the design, the clock is required to meeting certain goals. What are the certain goals? This is one of the most important step in physical design. So the clock net routing gets fixed and all the sequential elements gets timed accordingly. So tool uses various algorithms for building clock trees, basing of locations and also clock ports and the distance from clock pins. Normally, tool also synthesizes and optimizes the clock trace in CTS trees. And so during CTS, the tool what tries to minimize the DRC violations and takes care of area, power, and routability of the design. So let us define the CTS. If you see, this is the clock source, this is the flop. So in the CTS, what we do is in the earlier days, we are using the normal clock tree structure. In this clock tree structure, the main clock is going to some other flops, some other buffers. Through these buffers, there will be some other buffers. From buffers to here, there will be some clock gating cells and also muxes. Why you are using clock gating cells means there will be more dynamic power consumption. To decrease the more dynamic power consumption, we are using the clock gating technique. This is one of the technique in the power reduction. So by using a clock gating and muxes also, the clock tree is building from clock source to these flops. So if you see, this is the old structure from here to here, here to here, like this is the connection. These are the clock tree cells. We call it as uh, clock tree cells. These are the nothing but clock buffers, nothing but sync. This is the source. There will be source transition and there will be sync transition, and this is are the flip-flops. So in this algorithm, what we'll do? So in this, the source may have one transition, the sync may have one transition. So this algorithm, what we'll do is from source to destination, depending on the transition. As I said in place, here is also there will be some transition, clock transition. So, but depending on the clock transition, the route buffers will done. So from here to here, if you consider one route from here to here, this if it is 100 microns, you can if you give the tool to 0.5, at 50%, the tool will place the root buffer, the normal buffer. So from here to here, there will be one buffer. From here to here, one buffer. Like this, the tool is placing buffers from here to here. So these are the sync buffers, these are the flops. Once and also in this the routing algorithm, what we'll do is there will be ignored pins in fixed pins and ignored pins. So what is ignore pin? If you see the routing algorithm, the clock is tree is building, the routing for clock is building from source to flops like this. If you set any ignore pin like this, then the tool will not optimize this locations. If there is any maximum transition also, the tool will not touch this net. So why it is fixing just ignore pin? So before going to this transition, in the CTS mainly we are focused on uh, skew and latency. So the latency is nothing but from this clock source to this distance. This is the latency. So to minimize the latency, the routing algorithm what will do is it uses the buffers, and also it should be skew should be less. So this is the old technique. What is the disadvantage of this technique is, if I see from this to this, the number of cells are more from here. Because of this, there will be more number of cells, there will be more delay. So to overcome this, we are using multiple techniques. One is there is a fishbone technique and cross and also H-tree. We are in the CTS, what we are using the H-tree clock network. How the H-tree I will explain. So and also if there is more cells, there will be OCV. OCV is nothing but the on-chip variation. So in the clock path, when the chip is in operation, due to the air temperature process, there will be some delays will be acquired. So if there will be more cells in the clock path, there will be more OCV. So if there is more OCV, what is the problem? The cell delays may vary. If it is the launch flop, if it is the capture flop, if the cell delay is more here, the launch delay is more. If the launch delay is more, there will be setup timing violation. There will be setup and hold timing violation. I will explain later stages. So there will be some timing variations. So as much as you need to decrease the delay from this to this, there is nothing but we have to decrease the latency. For particular technology, there will be particular delays. In latest technology, we are using 120 PS is the minimum delay. So like that, the delay should be less. So there will be so many algorithms. So just I am explaining one of the best algorithms what we are using right now. This is H-tree clock network. So if the paths are perfectly balanced, there will be no clock skew. Ideally, the clock skew should be 0. Nothing but the latency between all the flops. From here to here, the latency should be same. If it is 100 microns, 100 PS, it should be 100 PS. Then it will be better. And also with less number of cells, it should follow. So to overcome this, what we will do is, this is the clock. This is the clock tree cells. From there, if you see, these are the flops. So in the list is how can you connect? This is one like this connection. This from depending on the area distance, you can place the cells. Now instead of going directly this clock to these cells, we are placing one root buffer here, like this. Here one root buffer. If you see, this is the P0 is the clock port. If P1, P3, P2, P4 are the clock root buffers, we are doing the routing from here to here same. That is common global connection. We are making as the in this algorithm, what we'll do is this H-tree algorithm, instead of individual routes, it make it as a single route from here to here. Then the delay is same for all these routes. This is one route, this is one route, this is one route. Here till this route, we are counting all the nearby cells. So if you see this is one route, let us consider 4 cells are here. These 4 cells connected like H. Everywhere the H-tree is following. So it should divide the total delay into the equal manner. Then what is the use? So the delay from here to here also same. The delay from here to here also same. So the delay is less. The total delay is less. So latency is less. So we are using this as a H-tree. So can insert clock gating, and also you are using the gated clocks. As I said, the gated clocks will reduce the power. So then what is the advantage due to this H-tree? So the exact zero skew in terms of distance due to the symmetry of the H-tree you can achieve. So for very special structures like top level clock level distribution, we are using this H3. In the block level, we are using the normal structures also. In the top level, there will be more area, there will be more nets. That's why we are using top level and then distribute it to the different clock sinks. So this is okay. If there is an advantage, there will be some disadvantage also. Like, what is the disadvantages? The blockages can spoil the symmetry. So actually, we can block in the design. There will be some blockages adjusted. There will be some in some area. Thus, there will be no cells presented. The designer issue. The designer will give the some blockages to utilize the area later. So at that time, if the blockage is adjusted, this cell cannot place here. Then this cell may place here. This cell may place here. At the time of blockages, the symmetry may spoil. It may or may not, but it's not correct. A guarantee. So this is one of the disadvantages, and also non-uniform sink locations and varying sink capacitance. So the sink is varying from year to year. The capacitance also varying. So with that also the delay will increase and also the power is varying. So this is one of the secondary clock buffers. If you see, this is the clock tree. Here one root buffer. This is one root buffer. This is the total design. What you are like this. This H3 algorithm will work. This is the CTS. So if you come to the signal routing, this is the major and lowest step in PNR. So in this major, what is the aim of this algorithm is the routing, what is assigned to the particular route region should be 100%. So the 100% connections should be adjusted. And also, even those are the 100% connections, it should minimize the total wire length. So it also, while doing routing, tool follows the SMART algorithm. This is one of the algorithm right now what we are following. One is what is SMART? This is signal integrity aware. This is manufacturing aware, area aware, routing aware, and timing aware. Okay. So in the signal integrity aware, what we are doing is, if you consider routing from year to year, this is source, this is the target. So maybe there will be some blockages from here to here. There is connection. So in the signal integrity, what we are calling as this is the one net. We call it as aggressor. This is one net. We call it as victim net. So if the two parallel nets are going long distance from here to here, there will be some coupling capacity adjustments. So if it is rising, actually in the signal integrity how it works is, here clock is adjusted, here is clock is adjusted. If this clock edge is rising, this clock edge is falling, there will be no issue. So there will be some coupling capacitance, less coupling capacitance. It is rising, it is falling means it is charging, it is discharging, no issue. If there is issue. If it is charging means it is discharging. If both are in same direction, if this is rising means both the cells are charging this capacitance. Then there is no issue. We can get more. If this is discharging, it is also no problem. But if it is rising, it is falling. So this cell is charging this capacitance. This cell is discharging this. Then this is the aggressor. This is the victim. Then what will happen is there will be coupling capacity adjustments between these layers. This is one layer. This is one layer. So due to the coupling capacitance, the power will drop. So if the power is less, automatically you get the less delay. If this cell need to get 5 volts, but due to this voltage drop, this may get less voltage. So to decrease this, the signal integrity should follow main rule. There will be more spacing between these aggressor and victim nets. So in real designs, there will be more victims and one aggressor. So how can you work on this signal integrity means? Let us see here. This is the one track. This is the one track. From initially, actually we can check the what is the victim net, what is the aggressor net. There will be tools. By using those tools, we will check the what is the aggressor net, what is having more coupling capacitance. So based on those nets, we will follow some rules. I will place one net here, one net from here. So we will use two spacings or one spacing. So if there is more spacing, the coupling capacitance is less. If the coupling capacitance is less, If the separation is more, the coupling automatically decreases capacitance. So if the capacitance decreases, we can decrease the delay. So that is one of the technique to decrease the signal integrity. And also one more thing is we are using the track 2x wide 1x metals. Nothing but if you use this metal, this is only having some width 1x, some other having 1x. So track 2x wide 1x means you should follow one route to another route, two tracks. So this net should be routed from here to here by utilizing two tracks. Then what will happen? Here also the spacing will be more. This is one of the technique the algorithm will use. Okay, so one thing. Another thing is we'll use the shielding. What is the shielding is actually if you see the signal nets, there will be some special nets. Those special nets need to be routed in higher layers. That is the designer plan. So for that we may get the cross stack. So to decrease the cross stack, how can you give the tool to use some techniques, some shielding technique. By giving the shielding technique, the algorithm will work on that shielding. How the algorithm will work on shielding? So initially, this is the signal routing. Along the signal routing, we will place VDD and VSS here, the power nets. So if you place the power nets, to power net and signal net, there will be less capacitance. Why? Because this is higher layer, this is normal layer. So the coupling capacitance is decreasing. Another net will not touch, will not go from here to here. So we are protecting this net from other nets by giving the shielding. So if this is the net, by giving some space, we are giving VDD here. We are giving VSS. We are giving VSS only ground net. So if you give the shielding here, the other signal net will not overcome this shielding net and will not penetrate into this net. Then also we will decrease the signal integrity. So this is one of the technique. By using the shielding, how can we give the shielding is, so actually we will select the nets, but we will initially remove the nets. Initially these are having the default rules. What are these rules means? Actually we are using the default rule track 2x wide 1x metal and also track 2x track 1x wide 1x metals. Like that there will be some metals. So how the metals means the default is nothing but if you route one route here, we can route another route in this track. That is default. There will be no issue. But if you give the track 2x wide 1x metal, so this metal should be the another metal should be route from here to here, giving two spaces, two tracks, and also track 1x wide 1x means uh, only one track, but the wide is 1x, and also some having more width. If the width is also more, there will be less resistance, right? So like that, we are using the different techniques. So with that also, by giving the routing rules to the routes, the algorithm will decrease the signal integrity. So this is one of the technique. So one signal routing is also done. Signal integrity, we can decrease the signal integrity as I said earlier. Okay. So one signal integrity, this is one of the main. After that, manufacturing aware. What is manufacturing aware means? So as I said, in the manufacturing process, the metal should not meet. The metal should not meet here. If I consider one track here, one track, one route here, one route here. If it is M1, this is M2 layer. This is also M2 layer. Why? Because the cell may have pin connection in M2. This is the internal hub M2. So if it is M2, this is M2. In the manufacturing, it may have so many issues. So these metals may connect in the lithography. By giving lithography, the ideally should be like this. So the metal should be equal in all areas. But when doing manufacturing, these metals may be met. So this type of aware also the tool know. So then what we'll do is tool this will go down, this will go up. Like that also this algorithm will work. So that is manufacturing aware. What we are calling as manufacturing aware. So with this, the router cannot connect to the here to here potential VR to VR DRC violation. So I will explain what are the DRC violations and how can you overcome it. So In this also, in the manufacturing, we have dishing and erosion violations. So actually in the process, there will be lithography, chemical, mechanical polishing. There will be some steps while designing chip. So in the chemical, mechanical processing, once the metals are ready, how the metals are used, actually they provide the one metal layer. After that, where there will be oxide like that, oxide. On that oxide, they will give the lithography. Lithography is nothing but they expose the light to where we need to insert the metal on that oxide. On that metal, so once lithography is done, they will do insertion of metal. So that is nothing but metal insertion. Once metal insertion is done, so like that they are manufacturing the cells. So at that time of once the metal polishing, when the metal is done, there will be mechanical, chemical, mechanical processing is done. The polishing is nothing but some may have some metal bits, some high, some lengths. So to get all this ideal. So while polishing, this metal should be ideal, but in the real, there will be dishing and erosion. So what is this dishing? So if there are multiple nets in a single area, while polishing, this metal may erase like our teeth. So this may be so many metals. This is nothing but dishing while doing chemical mechanical processing. And also there will be erosion. What is this erosion means? If I have one metal, it may have less at this area there will be cut edges. This is also one of the issue, dishing and erosion. To overcome this also, what we do is we are doing the metal filling. How can you metal fill means? So if this is the routing registered here, so we are inserting the metals. So there will be metal density rules. If we are having 10 metals, we are checking the metal density everywhere. We are checking the M1 density in a particular area. We are checking M1 density and M2 density, M3 density. Like that, we are checking the multiple densities. If the density is less, there will be erosion and dishing may occur. So what we will do is, okay, we are considering this is the area. In this, we are considering the 10 metals. Let us consider 10 metals. But according to the metal density, the ratio should be, let us talk for 10 metals compared to other total density, it should be 10%. By having it 10 metals, it may be 2% or 3%. It is less. Then what we are doing is we are inserting the metal fill. Metal fill is nothing but there will be no connection from one route to the another route. But we are inserting metals. There is nothing but a floating. What the floating may not have any connection. Okay, so we are decreasing the metal. If there is any less metals, we are inserting the metal fields. With that, we get the metal density more. If you are having the more metal, what is the use? If you are having the less metal, what is the use? Okay, if you are having the less metal, there will be, as I said, dishing and erosion. If you have less metal, if there are multiple metals beside these real metals, while doing dishing and erosion, the real metal may not disturb. Slightly may disturb, but not mostly. So by giving the metal pills, those are come to this, and there will be more impact on this metal piece and less impact on this metal piece. By using metal piece, that is the advantage. So there will be some metal density rules. So according to these algorithms, there will be 100% metal density. Even 100% metal density or in real life it should be 100, but 60 to 70% or 80% is also okay. So by giving 60 to 70% also, we get the metals. So by using the metal piece, we will get the real metal density. So this is one of the routing algorithm using this. And also, as I said, signal integrity, manufacturing evidence, area aware. How the algorithm will do area aware. If we consider, as I said, this is one, from here to here, there will be more cells, more area. If there is more routes, more area. So if you decrease the routes, the less the area is anyone talking? Okay. Yeah. If there are less number of roads, the area should be less. So the algorithm what will do is it will give in optimum locations with less metals. So by decrease the metals, the area is decreasing. That is nothing but area aware and also routing aware. What is routing aware means? If you consider this is one of the if this is major routing, from here to here there may be long net length. But in this timing, this aware routing aware means it will connect from here to here these by using this. So that's why we are not using major routing, but we are in detailed routing. What will do is it will connect the metal from here to here by taking the smart way, means it is giving the short distance. So that is nothing but the routing aware. Last thing is nothing but timing aware. So in this timing aware, what we'll do is, let us consider this is one flop, this is one flop, and this is the combination logic. Let us call this as a launch flop. Let us call this as a capturing flop. So the total clock from here to here, it will go. So there will be delays, clock to key delay and combo delay, and this also capture flop delay. So what the tool in this timing aware, that the tool what will do is actually there will be two checks over here in timing. We are checking for setup timing and hold timing. What is the setup timing and hold timing? I will explain. Let us consider this is the clock of the launch flop. Let us consider this is the capture flop of the clock. So the data launched by this clock should reach the capture flop within one clock cycle. This is one clock cycle. So let us consider this is the A, this is the B, this is A, this is B. So this data should reach from launch to capture. This is the red line. This is setup time requirement. So this is one of the timing requirement. So the data launchable launch flop should reach the capture flop within a single cycle. This is setup time requirement. And also it should be stable. So if I consider the combination logic is more, as I explained in the earlier session, if let us consider this is the 10ns, this is 1ns, this is 1ns, this is 8ns, this is 1ns, but the total 10ns is not optimum. There will be uncertainty also. So it should be less than 8ns, like 6ns. So if it is more timing delay, the data launched from here may capture next clock edge. So that is not good, right? So we are giving the one clock cycle, nothing but one frequency. If it is not meeting this frequency, it is not good. So what the routing algorithm will do is, so it will optimize the delays as much as less in this combination logic. If it is due to the cell delays, we can't do anything. So we need to inform to the top level team. So if it is due to the net delays, the nets will optimum by using this algorithm. So this is one of the setup requirement. And also it should follow the uncertainty like cross-check, OCV, all these things need to follow by this algorithm. And also there will be hold checks. So setup is check is nothing but the stable data should be present from here to here. If you give 0 here, the 0 should reach here, but not 1. So the data should be stable. Even it is changing from here to here anywhere, the data in this window should be stable. That is setup requirement. The hold is nothing but the data launched by this edge should not capture by this edge, right? So if I'm giving one clock cycle, this edge is the previous launch edge. This is the current capture edge. Previous to current is good, but previous to previous is not good, right? So the data launched by this edge should not met here. This is one of the hold check, and the data launched by next cycle should not capture in previous cycle. This is one of the hold check. So this algorithm what will do is the data, the timing error. So this is nothing but the timing error. It should follow setup and hold. Like this, the algorithm will do. Okay. So once timing error is done, so algorithm is also done. In this detailed routing, this is the final stage of routing. What I'm explaining. Actual geometric layout of each net is done within the assigned routing regions. So in the global routing, So let us consider this is the global routing, this is the detailed routing. In the global routing, I said this is the logical connection. It assumes from here to here, from here to here, from here to here. But in detailed routing, the connection should be correct. It should be physical. So from here to here, one vertical, one horizontal routing. This is one vertical, one horizontal routing. Where is the intersection point is done? There is one VI is adjusted. Like that, we are doing the routing. And also, so in the detailed routing, we are using the routing plan, track assignment actual to the metal. So in the logical, there is no actual routing, but here it is 100% routing. The main goal of detailed routing is nothing but it should interconnect all the nets without any shorts or spacing violation. I will explain what is open and short and spacing violation. So and also the detailed routing starts with the router dividing the block into specific areas, as I said earlier, like switch boxes or S blocks, which are generally expressed in terms of G cells. For example, 3 by 3 S box is a box which encompasses 9 G cells. Nothing but let us consider this is one box. 1, 2, 3, 1, 2, 3, 1, 2, 3. So the router is this consider this is one G cell, this is one G cell. In detailed routing, initially it takes in logical, it may be connected like this, it is logical connection only. But in detailed routing, from this cell pin to this cell pin, initially it starts on horizontal track. By giving horizontal route, it will check the all the surrounding nets. There should be less cross track, and also it should follow the minimum width and minimum spacing rules. So if I consider one metal width, so in our designs, what we are using the 14 metal tracks. One is the less track, less width, less spacing, and also 3, 4, 5 are the having the same width and same spacing. From 6 to 12, we are using the same width and same spacing, and also from 13 to 15, we are using 15 metal stack. We are calling it as a metal stack. For 15 metal stack, what we are using the 13 to 15 is one width. As I said, for a top layers, we have to use the power layers. So, but depending on the power clock, we are using the metals. So in the detailed routing, it will do horizontal routing. It will follow one via here. It from here to here, it will use vertical track. From here to here, it is using horizontal track. Okay, and also if two roads are adjusted here and here, yeah, this is the real connection in our designs what you are using. This is the VDD and VSS. These are the signal nets. So what we are following is, so this is the top net, like let us consider M13. Here we are using the VIA stack. So M13 to, let us consider this is M12, one VIA. From M12 to, there will be some other power routes, M11, one VIA. And also if there is cell here, this is M1. From M12 to M1, there will be multiple VIAs. So like this, we are doing the routing. Okay, this is done. And also, if there is the, we can use, if you are saying that one via, if any, with any issue, if the V is broken, what will it do? That is also problem. Okay, but to overcome that, what we are using in the multi-stack vias. So what we are using is like uh, here, if we consider same net, we are placing one via here, one via here, one via here. So we are using multiple vias and multiple routes. Then we can decrease the resistance, right? So by dividing the total routing into the multiple layers, we can decrease the resistance. With that also, we are decreasing the delay. So so once routing is done, we may get the IR issues or IR drop. So to overcome this IR drop issues, what we'll do is we are using the multiple layers instead of single layers. So if you can say this is the VDD VSS, we are drawing, this is the one power stack, this is one power stack, and also we are giving the one metal to all the powers, all the power nets. So we are nothing but we are taking the power from different metals, I mean different tracks. Like that also we are getting the more power. If we are getting the more power, there will be no issue. That is one of the technique. And also some other technique is, if you use, let us consider two cells over here. If let us consider these two cells are utilizing this metal stack, this power stack, then what we will do is, so we are moving this cell to the center of this power. actually there is one tool, voltage tool. The voltage tool, what will do is it will give the all, it will calculate all the power for any cell, and by depending on the algorithm, it will generate the reports. This cell is having more power, this net is having more power. So then what we are doing is we are checking for the power. So if it is, there is no issue, we will distribute the power to the this cell more power. If it is having more width, we will use more stacks here. If it is having less width and also it is sharing with one other cell, we are moving this cell to next area. Then also the power is divided. This is also like that we are using. And also one of the technique is if it is having high drive strength, nothing but the higher drive strength means having higher area. So it will occupy more power. Then also what we are doing is we will downsize that cell. Nothing but we are decreasing the drive strength of that cell. That is also one of the power technique we are using. With that also we are decreasing the IR issue, and also like this we are decreasing the IR, and also there will be LVS issue also, opens and shorts. The algorithm what will do is in global routing it may not check any LVS, I mean any opens and shorts, but in detailed routing what will do is, so if there is any net, so if it is connecting with other net, if those are different nets, there will be no issue. Why? Because one net is here, one net is here, those are in parallel. By seeing in top view, it may be both are connecting, but real life they will design the M1 first, then VIA1, then M2, then VIA2, like that they will manufacture. So these are parallel having more space. So with using VIAs, there will be no issue. But if M1 is crossing another M1, then there is issue. So the global routing what will do is it will mostly it will avoid the shorts. So if if there is no road, there is no area, then may short occur. So at that time what we are doing is that is not possible with this algorithm, the global routing algorithm. Even the algorithms also will do up to certain range. Over the range, it will not also do anything. Then what we'll do is just we are checking the possible nets. So if we are having short here, so what we are doing is we are moving this net using different layers. If there is a space, we are moving this net to the next track. If there is also no availability, we are moving this like this. We are moving from one to one. So there will be more manual work here. If there is issue like that, we are moving one metal to the some other area. With that also, we are we are decreasing the shorts. Okay, if there is no short issue also, if there is no open issue, when the open issue, if there is cell is adjusted here, if there is a blockage, routing blockage is also adjusted. When we are using routing blockages means, so so if one cell has routes, more nets, more pins. So if there is more pins having more metals, let us consider M2, M3, M4 pins. So at that pins having more pins means there will be no space. So then tool what will do is it perform routing blockage on that pins above the M2, M3, M4. Then the routes are having only M2, M3, M4. Okay, if there is any M5, so it will not go here. So there will be some open adjusted. At that time, what we do is, so we are moving that net through some other area. Like that also, we'll fix the open. So it should be LVS clean. Nothing but open short should be clean. And also, we are using the layout versus schematic. Actually, what you are doing this is the ICC or Innovus tools. In Synopsys ICC, in Cadence, we are using Innovus tools, but those are not sign-up tools. For sign-up tools, we are using multiple. So we are using caliber tools. Caliber tools are nothing but sign-up tools. Sign-up tools will check all those things. Okay. So by depending on this also, we'll do global routing. So once everything is done, this detailed routing is done. So there will be some constraints. So what are the constraints means? We need to guide the tool during routing. How? So there will be some conditions we will give. So you need to use some transition, some capacitance, and also you need to use for if you consider the clock nets, those are more. For those clock nuts, we are using the track 2x, wide 1x. So the constraints to be set are as follows, like set don't use, set don't touch. There will be some constraints, and also setting the maximum length for the routing wires. Means if you use the there will be maximum length, means if there will be signal integrity issue, crosstalk issue. So for that also we are setting the maximum length ratio, and also set stringent guidelines for minimum width and minimum spacing. As I said, the one you need to decrease the width as much as possible and spacing as much as possible. So you need to set the stringent net, and also the set preferred routing directions to specific metal layers during routing. What is this preferred routing direction means? If you see, this is the horizontal, it will follow only horizontal routing. If it is vertical, it should follow only vertical routing. But we can guide the tool that this vertical routing may use as horizontal, but not optimum, not more. So when these cases, this is one routing. So if all the tracks are filled with all metals, then we can't do anything, right? So there is no space. At the time we can't do anything. At that time, we can use these vertical layers as horizontal layers, but not touching with this horizontal. And by following the minimum spacing, by giving minimum spacing, we can route these algorithms. That is nothing but the direction. So it may not be only vertical, it should be horizontal, but only for particular layers at particular area you can use. That is one of the technique. And also okay, and also blocking routing in specific regions. When you are using blocking routing, so as I said, in some area I am having more congestion. At that time I can't do anything. So all these are at the earliest, not in the earliest stages, in the last stages. So once placement is done, once CTS is done, we cannot go back at that time. Already there will be so much of time is wasted. So at that time, what we'll do is we are giving the routing blockage. We are using the routing guides. Nothing but so in some area. So let us consider this area. If I having more area here, more net tracks available here, we will define a routing guide here in this area. So we are giving such routing guide, but you have to use M1 or M2 or M3 only up to 50%, not 100% or 60%. If you give the 60%, it should use only 60% of routes. So if there are 10 routing tracks available, it will use only 6 routing tracks. If you give for 5, it will use only 5. Like that, we are giving the routing guides to the tool to follow just minimum routing rules. So minimum routes at that area. That is also with that we have so many issues. What is that? Earlier the routing is done from here to here. That is shortest distance. But now what you are doing? You are giving routing guide here. If you are giving routing guide here, the routing may detour from here to here. Then the net length may vary. The net length may increase. With increasing net length, we get the more delay. That is one issue. So at that case, what you are doing is we are using there will be some VT types. I will explain. Low VT, high VT, medium VT means VT is nothing but threshold voltage. So if there is less voltage, less threshold voltage, there will be less leakage and less power consumption, LVT cells. But they're having high delays. And also if you're having, there will be LVT, standard LVT, medium LVT and high LVT, ultra LVT. So in this case, what you are using is there will be more delay. This path may increase, the delay may increase. At that time, we are convert this cell to the ULVT cell. If it is LVT cell, we are convert to the ULVT cell. Means the delay will be less to this cell. If the delay is less, the timing variation is less. So like that, we are doing the VT swap and after routing also. After routing, there will be opt-out stage. At that opt-out, we are doing this technique. So like that, we are giving the routing guides here, and to overcome that issue we are using the ULVT, nothing but VT swap technique we are using. And also by using VT swap technique, it should be mandatory to follow the rules. So we can't use all the type of VLT cells, LVT cells. So there will be some percentage for the design. The designer where they give for us to, we have to use only 1% or 2%. So we are working on 3 million or 4 million cells. So about 4 million cells, 1% means so it should be 40,000 like that. So we should not, we should maintain all the cells, not only in the design. After that design, we have what is that functional ESOs also there. At the functional ESOs, at the last stage, they will insert the flops or cells in the design, but they did not go into the initial stage. There will be some base tapeout. Once there will be base tapeout and metal tapeout. The base tapeout means nothing but the connections. What are the existed for the pins cells? There will be, if it is the M1 or M2 till M1, the road should not touch once base tapeout is done. So in the initial shells only, by depending on these algorithms, we are following all the rules and we will design the designs. So once base support is done, we are not touching the lower layers, we are touching the only higher layers. So in the higher layers only, you need to follow whatever it may be. So that is the that is after base tapeout. After base tapeout, there will be metal tapeout. In the metal tapeout, what we are doing is we did not touch any metal. Okay, so once metal tapeout is done, the design is done. So between BTO and MTO, there will be some IR drop also. So to overcome that IR depot, we will insert the metals in parallel to these adjusted metals. So like that, we are doing BTO and MTO. So this is nothing but the uh, routing, blocking routing in specific regions, and also setting limits on routing to specific regions. So if you consider the notches, at the notches there will be more routing. So at that place, what you are using, you do not route there. So in specific regions, you do not do routing. So like that also, we are giving the limits for routing, and also setting precedence to routing regions. So what it means is, so initially you need to do routing here. After that, some other area like that also can do settings, and also constraining the routing density. We can define the density. As I said, there is 100% density. If there is more density, there will be more routes. So we will give the 0.5% or 0.6% in critical areas. That is nothing but the constraining the routing density, and also constraining the pin connections. If we consider a normal cells, buffers are having only two pins. If we consider AOS cells or OAS cells, those are having more pins. At that time, there will be more routing. Even by using these algorithms, we can't met all the issues. So we are considering the pin connections. So nothing but we are giving the hollows like spacings, or also we are giving the some area to these pins. Like that also we are considering the pin connection. And also we are restricting the degree of rerouting. What is this degree of rerouting means? So once the routing is done, so we cannot go back any multiple times. At that time, what we are doing is we go forward. We are taking that database as annotated to the next previous stage. We are giving that database, and also so the fixing is taken in earlier stages by coming back. It is back forwarding. That is nothing but the degree of rerouting. So so by doing multiple back annotations, we are restricting the degree of routing. So these all are the routing constraints we are following while doing ASIC in ASIC, depending on the routing algorithms. And also, let us consider two the same. This is with more weights, with less weights. What it means? So if you see here, this is one layer, this is one layer, this is one layer. This is horizontal, this is vertical, and this is horizontal and vertical. So in these cases, it may be better, or this may be better. So if this is a small length, it is better. There will be no issue. If it is small length means a small resistance, small capacitance, or small delay. But if it is long net length, this is not good. Why? Because there will be long net. If there is long net, preceding nets may have more signal integrity. So at that time, what we are doing is we are doing jogging. Jogging is nothing but layer hopping. Layer hopping means if this is metal 1, if this is metal 2, if this is metal 3, instead of using one metal, what we are doing is we are doing the metal hopping. So we are forming metal connection here. We are doing vertical connection. We are doing some other metal connection. With this, we get the less signal integrity, and also by doing chemical mechanical processing also, if there is only one metal, there will be so much of erosion done, so much of dishing done. By using multiple layers, we can decrease this erosion like that. And also there will be antenna effect. What is the antenna effect means? What I explain, if you there will be some, while doing the manufacturing, there will be some ratio. You need to some follow antenna ratio. If there is more than antenna ratio, the metal may be burnt out. So there will be more bulges also. So to overcome that also, we need to follow antenna ratios. Antenna ratio should be less. By doing layer hopping also, the antenna ratio is less. And also, if there is crosstalk or any uncertainty existed, by giving a layer hopping, so if you are going from one layer to other instead of one layer, so if there is connection, there is any area, we need to use less joggings. So that is also we are taken about routing. This is all about the routing algorithms. So the main goal of the routing is you need to minimize the total interconnect or wire length. That is one of the technique. As the algorithm, what will they do? So the interconnection should be less, and also the maximize the probability that the tool can complete routing. So it should be 100%. It should not give 20%, 30%. There will be some test. We are checking spec annotation. The spec annotation is nothing but we are checking the every net should be routed 100%. If the spec annotation base is less than 100%, we will go back and we will check and we will do again routing. That is one of the test. Okay, and also the probability should be more, and also minimize the critical path delay. If we having the more delay due to the resistance capacitance, we need to decrease the critical path. So by taking the advantage of next path, we need to decrease the critical path of delay of that net, and also minimize the number of layer changes. As I said, the VS should be less. Why? Because if we having, I mean, it should be optimum. If we having more VS, so there will be more cost. So you need to follow timing. At the same time, the manufacturing cost also should be less. So you need to follow the minimize the number of VS, and also you need to complete the connection without increasing total area of the block. So even if you give the some block area, you have to use that area only. It did not use more area. So you need to complete the connections without increasing all that area, and also meeting the timing DRCs and obtaining good timing QR. So as I said, DRC is nothing but the minimum width between two layers is need to follow, and also there will be some spacing, some length. There will be so many DRC rules. We are having the DRM. DRM is in our designs. We have DRM file. In the DRM file, for every layer, we have DRC techniques. It should follow minimum width, minimum spacing, and minimum length. We are following all those things. So you need to follow the DRM. You should meet the timing DRCs, and also good timing QR. QR is nothing but quality of result. So nothing but you need to follow the minimum best timing. So the timing should not be more. The timing should be less, and although the DRC should be less, minimizing the congestion hotspots. As I said, if there are so many cells in same area, that is the hotspot. So you need to spread the cells. That is one of the minimizing technique. And also SI driven. SI is nothing but signal integrity. So you need to the reduction in the crosstalk noise and delta delays. As I said, crosstalk is due to the coupling capacitance, and the delta delays is nothing but the by changing the difference between delays. So if you're having cell delay of 1 volt, it may be 0.9 volts. So actually you should follow the 1 volt, but if you're getting 0.9 volts, the delay is zero, the delta delay is 0.1. Like that, we are following the delta delay should be less. So like that, these all are the goals of routing. We need to follow all these techniques, and also there it should be any DRC free, and also LVS free, and also LEC free. Like as I said in earlier session, logical equivalent check, and also logical equivalent means every stage the logical connection should follow. Even in detailed routing or global routing, it should follow. So by taking all these steps, we need to do routing. Though algorithms are useful in this as I said. Thank you. Anything? Hello.
Thank you, sir.
Sir,
Yeah.
Sir, is there any queries in the chat box? Prasad Garu.
Ma'am.
Is there any queries in the chat box?
Yes, madam. Yes, madam. We have some queries.
Yes, sir.
Sir, should we go for queries, sir?
Yeah, no, sure. I can, no problem. If more queries, you may mail to me. There will be no issue. I will give you answers later also. There will be no issue.
So the participant can ask the query directly. No issue.
Yeah, no
If
issue. No
participant
problem.
is online, they can ask it query directly.
Yeah, sure.
If anyone is having queries, you can unmute yourself and you can ask the queries. Otherwise, you can contact later. We will share the details of a resource person in the group. Okay, I think no one is asking, ma'am.
No
Yes, sir,
issue.
we
You
can.
can give me anytime. I will. Okay. Just you can mail
Yeah,
me.
if
I will answer
there
all
is
the
any
questions.
query, we will mail you, sir.
Yeah, sure, Andy. No problem. Anytime I will.
Okay.
You can get mail from Vasdev. He will give you the
Yeah,
mail.
we have.
Like
We will mail you.
Yeah, sure.
Prasad Garu, you can conclude.
Yes, thank you, madam. Good evening, sir. Good evening, sir.
Yeah, good evening, Andy.
Manikanta, sir. This is Dr. N. Prasad, Senior Assistant Professor in AC Department, GMRIT.
Yeah, thank
It's
you.
my privilege to deliver the vote of thanks for this 6 days ATAL FDP on VLSI design innovations for defense applications. First and foremost, I would like to extend my heartfelt gratitude to our chief guest, C.H. Manikanta sir, for gracing this event. It is delivering an inspiring and interesting topic on routing algorithms in ASIC. Your words have been truly enlightening and set the perfect tone for today's gathering, sir. And sir especially covered some topics, some important topics, like what is routing in ASIC, what is basic PNR flow, what algorithms required for placement like pre-placement algorithm, global placement algorithm, legalization, HFNS, DRV algorithm, multi-bit flop conversion, quick initial routing, and what is design rule checks, what rules are required, and what is the difference between this global routing and detailed routing. Really, all these topics are really useful for the participants, sir. On behalf of EC Department GMRIT, thank you, sir, for accepting our invitation and sharing your valuable knowledge. I would like to thank to our organizing committee members for their hard work and dedication in ensuring this event was a success. Thank you, sir. Thank you, sir. Thank you for all the participants for engaging your valuable time to attend this ATAL FDP meeting.
Thank you, Andy. Thank you so much. Thank you once again to Vasdev. Thank you.
Thank you. Thank you, sir. Thank you to each and everyone.
Thank you, sir. Thank you so much, sir.
Thank you.
Have a good night, sir.
Thank you, sir. Good night.
Thank you for all. Thank you.
So, dear participants, today for the day 4, we have shared the feedback link in the chat box as well as